frequency of the observer. load, we should be talking about current. It's a very common mistake, okay? But I would hope it's one that many of our graduates don't make, okay? So it's similar to the voltage is going somewheres and things like that, okay?
Yeah.
So
Yep.
again, my next question was going to be why did the resistor burn out? Then Mr. Parker kind of took care of that for me. Could you bring up your schematic,
Yep.
just the general, the one that has the Atmega and the regulator.
This one?
Hold on, let me just compare quickly here. Yes, I guess that's the one. I'm just curious. If you look at J3, for example, why does J3 have a wire going through it?
Well, it's because of a PCB. I didn't put the PCBs for the presentation. I can show you the PCB file. The problem with this ground, like this schematic is kind of mimics the PCB layout. And during the PCB design, like this jumper was essential because I need to jump across the ground because
Okay.
otherwise it's just trapped inside.
I understand that, but does a schematic, when we draw schematics, does it deal with the physical properties of the project, or what does it actually? It represents the electrical properties, right?
Yeah. Yeah.
So if I were you, you're right to have a component there called J3, okay, which again, to be honest, nowadays we use 0 ohm jumpers, or resistors, so you might as well just use the resistor symbology for that, okay, and list it as 0 ohms. But you shouldn't, like, if you would have had a resistor, you would have never drawn a resistor across the line like that, right? You would have put it positioned somewhere else, and that's what you should have done with this too. Okay, don't worry. Even J2 suffers the same problem. I understand what you're trying to show. You're trying to show the fact that jumper 2 clears those 2 traces, but those aren't traces. They're net lines that show electrical connectivity, right? So they don't have to be jumped over or anything like that. Now in your PCB, when you're going to lay it there, obviously then that's where the purpose of J2, J3 come into play, where they are actually creating a bridge for your traces to go under. Okay, so just because this, for me, that makes your schematic look unfinished, or needs more editorial changes because of that. Because nobody's going to look at that and say, oh well, that's because J3 is there for, because that's the PCB board side of designing, and the schematic, to be honest, doesn't really represent that. All right, the schematic is there for us to understand what the connectivity of the parts are electrically, right?
Yeah, I agree.
So, excellent. Okay, could you you had those 5-volt regulators there at the input there?
Here.
Was it that one? Yeah, it might have been. I didn't. Yeah, C1. So what's the reason for C1 and C2?
Well, it's from the data sheet. Like the data sheet specifically tells that you need to have the 0.22 microfarad ceramic capacitor.
Yeah.
And on the output, it does not necessarily tells that, but it's recommended to use it, which can help.
Okay. Do they tell you why though? Did you ever look into that? Because that's important to also understand why, to be honest. Because if we're talking about manufacturer recommendations, one other thing they recommend is a diode bridging pin 1 to pin 3 in reverse bias. And obviously you chose not to put it in. So, the question becomes, why follow 2 recommendations but not the third one? All right.
Yeah.
Okay. Did you see that about the diode?
No, honestly,
No?
I didn't see that. So
hold on, I can even tell you which page it's on, because I have it's on, if you look at page 13 of the TI datasheet for that particular device, okay? That family of devices. It'll show you that there's a diode there that should be installed across there. Okay, and the reason for that diode is because you're not allowed to make the input go lower than the output on these, or they'll destroy themselves. Okay. As far as C1 and C2, if I were you, I would go look them up to know what they are, what their purpose is. Okay, because they actually serve a very important purpose, and if they are not there, in some cases, your system will not regulate properly. Okay,
Yeah.
so it's all right. Anybody else? I don't think I know Mr. Broad is troubleshooting some connectivity issues there, so he's not available. And
maybe just very quickly,
sure.
since on the subject of C1 and C2 and your 7805, Andre, would you care to speculate as to what they might be doing? What
the C1, which ones?
Your C1 and C2 in and out on your regulator.
Well, like the as I remember the word, if I remember it correctly, the C2 is to help with the transient response or something like that.
Yep. Okay.
On the outside. While the C1, I will be completely honest, I'm not sure. Like I assume it's to help ensure the stable input voltage or something, but like beyond that.
That's what 7805 is for.
Yeah.
Can you elaborate a little bit more on what you mean by transient response for C2?
The 5 volts that is outputted, it needs to be like constant, and because the input voltage into the regulator may not be constant either, like that's what it does. But it's just a speculation. Honestly, I don't exactly.
Yeah, no, I don't think that's.
Yeah.
I'll give you a hint to both of them, especially the output there. The LM7805 and all of these families of linear ICs, they're basically very large gain amplifiers in the grand scheme of things. So there are risks to having very large scale amplification as a single stage, and that's what C1 and C2 are there to help stabilize. So you go look into that a little bit more. Okay. Mm-hmm. Obviously, if it's go look at what happens when you have large gain amplifiers, that are unstable. See what happens, and then that kind of applies to the LM7805. All right.
Okay. Yep.
I think we're out of time at this point, unless Don, did you have another question? Or
thank you, Andre. Good presentation.
Yes, good presentation. By all means. All right, so we'll take our 10-minute break and be back at 9:30. And at 9:30, we'll have Gosai explain his plant watering system to us. All right, so see you all at 9:30. Thanks. Okay. Thank you, Andre. Very good job.
test audio for Mr. Broad, troubleshooting the lack of audio in Teams.
Hello everyone, my audio and video is clear?
Yeah, you got a couple of minutes, Kushal.
Yeah, sure. I just need to check.
All right, so we're back. We're going to start a new presentation. We apologize this morning. We've had a little bit of technical difficulties on the stream with audio. We have our best man on there working the problems out as we speak. It should be cleared up by now, so our apologies for that. This morning for our second presentation, we're going to have Kusal Gosai talk about his plant watering system. So Kusal, are you ready to go?
Yes.
All right, so the floor is yours.
Thank you. So good morning, everyone. Today I'm going to talk about the automation field. So first, let's start with the advantages of automation. Like we can notice that nowadays everywhere automation is involved, like in our daily routines, in our vehicles, like in our daily routines, such as like what our water, when we go and fill up the water bottle, there is also the automation. So why we need the automation everywhere? Like what is the need for the automation? So first of all, it will increase the efficiency. In efficiency, I mean like whenever, for example, we go and fill up the water bottle without automation. Some people are too perfect, like they fill up the water bottle and they stop the water. That's it. They don't waste any. They don't waste any type of water on anything. But sometimes some people are not that much of perfect. They waste the clean water. So we can save we can reduce the wastage of clean water by automation. So that is also the one of the big advantage, as well as like it will reduce the human worries, stress, and efforts, everything. So here I involve the automation into the task of feeding water to the plant. So I'm going to share my presentation with you now. So are you seeing my presentation slide? Is
Yes.
it clear?
Yep.
Okay. So let's start with this good view. So my project is based on the water feeding system to the plant. So I made this in order to reduce the stress to feed the water. Like personally for me, feeding water to the plant is very boring task for me actually. So whenever I have to do this work, I feel too bored and like just turn on the water and do wait to feed the water. Like, is it okay or not? So this device, this system will remove all the stress, worries, and it will remove one of your tasks also. So I made this system in order to do this. So let's start talk about the presentation. So during this presentation, I'm going to talk about the objective of the projects, concept drawings, project model, project functionality, major components, and the technical drawings and diagrams, and then coding for the project. So let's first start from the objective of the project. So what is the main objective? Like, what is the main concept of this project? So main concept of this project is I'm sensing the moisture level from the soil around the plant, and according to that moisture value, I will control the water flow. So this is the main objective of this project. Like, and by this way we can feed the water very efficiently to the plant. Like sometimes it happens like we turn on the water and we forgot to turn off it, like, and sometimes we forgot to feed the water. In both of case, there is a risk to die the plant, and if we forgot to turn off the water, we will waste the clean water. So this device is perfect to remove all these things. So let's see the concept drawing of the device of this project. So there is the three views I mentioned here in this slide. So there's a front view, side view. Actually, that side view is for the left hand side of the device, and there is a bottom view. So on the front view, there is a LCD display where we can see the water pump status as well as moisture level. So overall, like it will shows the entire process of this project. So we can monitor whatever the status of the water pump and moisture through this LCD. And there is the two indication LEDs are also there, like power indication and water pump indication. In case like if we are far from the device and if we want to see the status, we can see through that LED because LED is brighter. So we can see that from that. And there is a power switch by which we can turn on and turn off the device. So this is all about the front view, and on the left hand side there is the connection for the power jack, from where we can supply the supply this device, power this device. So, and this is the and the third view is the bottom view. So here, so I did not mention the dimensions from the edges to this boxes and this circle, just because like this is just for the connection outlet for the water pump and sensor and float switch, and for the programming outlets. So we can make anywhere this this holes and this boxes. So I did not mention the distance from the edges. So this is all about the concept drawing. Now let's move forward towards the project model. So this is the actual model of my project. So this is the device, and here I install the connectors to connect the connections for the moisture sensor as well as the water pump. Moisture sensor and float switch, and these are for the programming probes. And here we can see that I just put my water pump and float switch here I just want to see this together, show this together. So this float switch and water pump will installed into the actual water tank, and this moisture sensor will be placed into the soil. So this is all about the my project model. We're gonna see the actual working into the demonstration. So let's move to the next slide. So now let's talk about the project functionality here. So basically I'm sensing the moisture level, right? So I'm sensing the moisture level through the moisture sensor, and then whatever the moisture value, it will transfer to the controller through this sensor circuit, and then according to the moisture value, the control will trigger the water pump, and this water pump will control the water supply. So this is the short and simple functionality of my project. Now let's move towards the major components which I used for this project. So I used this moisture sensor. It operates on 5-volt DC, and it has the analog output range from 0 to 1024. So we can get the different moisture values in between this range, like 0 to 1024. So this sensor I used, and as a controller of my project, I used Atmega controller, and this IC also requires 5 volts to operate, and this controller will control the entire process of my project. Now this is the water pump which I used to control the water supply. So it requires 6 volt to 12 volt DC, and it consumes 65 milliamps to 500 milliamps current, and it can transfer up to 550 liters liters water per hour. And these all data are from the data sheet of this water pump. But as per my practical measurements, I got the little bit different values, such as like on this, when I start this water pump, like on the at the beginning, I got like around 600 to 700 milliamps peak ampere. So according to that, it will consumes around like 7.2 watts to 8.4 watts. But after that, it will consume 470 milliamps when it will become stable. So, and on that time, it will consume like 5.64 watt, because I connected 12 volt. I'm supplying 12 volt to this water pump. So this all watt ratings are as per the 12 volt DC. So let's move towards the LCD display. Yes. So I used 16 by 2 digits, 16 digits by 2 LCD display. It also operates 5 volts DC. We can give the 3.3 volts DC as well as per the data sheet. And I use this LCD display, as I already mentioned, to monitor the water pump status and moisture level. So I use this LCD for the monitoring purpose of this process. And now let's talk about the drawings and diagrams of this device, like such as block diagram, schematic, and coding flowchart. So first of all, this is a block diagram of my project. So I start with this power supply blocks. So I use two different voltages for this device, like 12 volt to supply the water pump and this 5 volt to supply my controlling circuit. So here I added the 12 volt DC adapter and to the 5 volt, like 7805 5 volt regulator IC through this power switch, by which we can turn on and turn off the whole system. Like by turning off the switch, we can turn off the controlling circuit, so it will stop the entire process. So I connected this power switch here for this purpose, and I connected this LED one as a power LED, just to on the output side of this regulator IC. So this IC will supply the controlling circuit also, as well as this LED, this power LED also, to show the power indication. And now let's go on to the controlling circuit here. So this is my controller, which I used at Mega, and this sensor circuit will sense the moisture level through these probes from the soil, and whatever is the moisture values, this sensor will be transferred to this Atmega controller, and according to that sensor values, it will trigger this transistor through this float switch. So why I connected float switch here? Just for the protection of my water pump. Like if in case there is no water into the water tank, this switch will becomes an open circuit. So it will break the path and it will not trigger the transistor from the controller. So I connected this float switch for that purpose. But when there is a water, it will becomes a closed path and it will trigger this transistor, and this transistor will supply the 5 volt to the relay coil, as well as this LED 2 also. This LED will show the status of the water pump. So whenever this transistor will trigger, it will turn on this relay, and like it will energize the relay coil, which requires 5 volt to energize, and this relay will connect the path to the water pump to provide the 12 volt. So when this water pump operate, on that time my LED will be glow. So it will shows the water pump status that it is on or off. So I connected this LED here, and whatever the process, like the moisture level and my water pump is triggered or not, that everything will be shown here on this LCD through this Atmega controller. So this is all about my block diagram. Now let's see the schematic diagram of this project. So here is the schematic. Let me zoom in. Okay, so this is the main power jack from where I gave the 12 volt supply as a main source of my project. So here we can connect like 12 volt adapter, and on the positive end here I connected this switch. Like I connected this 12 volt to the 7805 regulator IC on the input, at the input side, through this switch, so we can control the entire power supply through this switch, like we can turn on and off. So it's for that purpose. And on the output side here, I got the 5 volts, which I use to power the Atomega controller IC, as well as to power this LED also. Like it is the power LED. So whenever we turn on the switch, this 5 volt will be go into this LED also, so it will shows the power indication. Now these all are the connectors for the programming. So in case if we want to do any modification after making the after placing this device onto the actual field, we just need to connect this 5 connections, and we can easily program this IC through the Arduino board. So I put this connections for that. And now this is my moisture sensor. It gives the analog output. So I connected this analog terminal to this IC on the analog pin. So it requires the 5 volts DC to operate. So I gave the 5 volt directly to the sensor. So this is all about the input side of this schematic. Like on the output side, I used 7-number digital pin of this controller. So according to as per the moisture level, whatever the moisture level this controller will sense through this moisture sensor, controller will trigger this pin. So whenever this pin will become high, the 5 volt will transfer through this float switch to this transistor's base terminal. So whenever this float switch will be closed, like as a will close, it will connect the path between the Atomega pin and the base terminal of the transistor. And so when this base terminal get the 5 volts, it will supply this 5 volt from collector to emitter to this LED2 and this relay coil. I use the SPDT relay. So it will gives the 5 volt to both of these things, like LED and coil. I connected this LED here for the purpose of to show the water pump status, as I already explained into the block diagram. So when this relay coil gets the 5 volt, this terminal will change from NC to NO, and it will connect this path from here to here, and it will supply the 12 volt to the water pump. So whenever here there is a 5 volt, it will connect this path and it will trigger the water pump as well. So I connected this diode as a flyback diode just to protect my controlling circuit from this from the back voltage from this water pump. And whenever there is no water, in the absence of water in the water tank, this float switch will becomes an open circuit. So it doesn't matter, like if this pin will trigger, but this path will be break from here, it will not let this process happen. So like this way I can protect my water pump from burning out. Like without water it will be burnt. It's a water pump. So without water it will not let this process happen. So I connected my float switch here. So this is all about the schematic diagram. Now, and these are the connections for my LCD. So this 3rd number terminal is for the contrast to set the contrast of the LCD. Like we can connect the variable resistor as well here, but I connected the 2 fixed resistors here at the on this pin, just because I want to get the fixed contrast of the LCD, but by connecting the variable resistor, we can adjust the contrast here for this LCD. So first I connected this very small value resistor here around like 220 ohms when I connected onto the breadboard, but after connecting onto the actual PCB, I need the really very small value of resistor, but it will not happen. The contrast, I can't get the proper contrast, so finally I used a jumper here, and I used the 10K resistor here to give the 5 volts. So this is all about the schematic diagram. Now let's move towards the coding flowchart. So this is the coding flowchart. This flowchart is about the coding. So it's very simple. First of all, controller read the sensor value, and there is a 2 loops. Whether like sensor value, like moisture value is below 450. Moisture value, it means like sensor value. It will below 450. It will turn on the water pump, and if it reach more than 840, it will turn off the water pump. So it's very simple process. Now let's see the actual programming. So here I did not put the whole programming. I just put my main 2 loops of the programming for this project. So let me explain the 2 main loops. So first of all, first loop starts from here. So when my moisture value is below 450, it will trigger the water pump pin, and also it will print on the LCD like water pump on and moisture level low. And on the contrary side, like if my moisture value will be greater than the 840, it will turn off the water pump pin, and it will print on the LCD that water pump is off and the moisture level high. So this is all about my codings. Now let me recapitulate my presentation here. So the first of all, this device is very affordable and convenient according to me, for every common person. Just because like it requires a very small place, like small space to install, and it's easy to use, and we can it will remove the or lots of worries to feel about the feeding water to the plant. It will do automatically everything for you regarding that tasks. So this system is very beneficial according to me. And another thing is like sometimes like I made this device for the domestic purpose, but we can use it for farming purpose as well. Like lots of time it happens, sometimes people overfeed the water to the plant, and sometimes they don't feed the water at all. In this both case, there is a risk to die the plants, like damage the plant. So but after installing this device, it will not happen. And another thing is that in the absence of person at the home, this process will be keep continuing, and it will protect our water pump from the water pump from the burning out. It will remove the stress also, because float switch will not let happen that thing, just because in the absence of water it will stop the whole process. So this device is beneficial for that also. So this is all about my presentation. So now I will show my demonstration of the project. So just a second. Can you see me now?
Not yet.
Okay. Okay. So this is my actual device of the project, which I already mentioned into the my model slide of the presentation. So here is my power switch. So I just turn on that. Is that my LCD digits are clear to read? Just as like because of camera. Okay, so I installed the float switch here, and there is a water pump here. I just put my water pipe just here because I don't want to put the water on the floor, so that's why. So like this way we can put the sensor into the soil. Like someone fit the water already here onto the pot, so it is right now it's wet, so it will not let pump to turn on here. We can see that here, but once we remove the sensor, so right now it says it's dry, so it says like moisture level low, and what right now my water pump is on here, so you can see here as an LED indication that water pump is on, and my power is also on because I turn on these things. Like if I turn off, see right now my sensor is not in there. It says it's a dry, so it says moisture level low and my water pump on, as you can see here. Now I will show you the operation of this float switch. Let me transfer this thing onto the. In the absence of water, it will be automatically turned off. Just give me a second. I will. So I don't have lots of space here, so I just transfer this water into the another thing. So when this water level decreases, it will automatically stop all the process. Right now, water pump is on because there is enough water into the bucket. So just more 10 seconds, it will be done. Yeah, so right now my water supply is turned off, and it says my water pump is off here because as like my water level goes below that float switch. So sorry for the bad video clarity here. So this is all about the a demonstration of the project. Okay. Thank you everybody for your crucial time. If any questions.
All right, thank you, Kusal. Excuse me, I got a frog in my throat. Great demonstration there. I think Mr. Broad wanted to start with a question. I'm not sure. Is Mr. Broad available? Oh, he's saying, "Give me a second." Okay, so I'll start with a few, and then he can jump in. Could you bring up your flow chart, please?
Yes.
Okay, so your flow chart is
Sorry.
demonstrating. The flow chart. Yeah, there you go. It's demonstrating a flow chart demonstrates the flow of the logic in your program. So we start at the top where it says start. Okay. We look at controller reads the sensor. You're missing an S there. So the controller reads the sensor value. Okay. That's fine. That's a process, right? And then again, we split up here. Why do we split up? Does your program actually multi-thread? Does it actually do that? I'm going to start using the right words
No,
here.
like I'm just trying to show the two different loops by this way. So,
but that's again, a flowchart is made for, it's primarily to show the logical flow, the sequence of events. So by splitting them up here, you're telling me, if I was trying to figure out your program, you're telling me these two parallel events are happening at the same time. Are they happening at the same time in your program?
like in program, it's constantly checking this two instructions.
No, what I'm asking you is those two events, are they happening at the same time in your program?
No.
No, they happen how? Which one happens first?
So it depends on the moisture sensor values. Like whether it's below 450, it will run this slow.
No. Which one, as you go through your program in sequence?
Yeah, so first loop is this 450, below 451.
So it tests for 450 first.
Yeah.
Okay, and then what does it do?
Then it will run this loop.
Okay, so why would you put them in parallel? They should happen one after the other, should they not?
Oh, yes.
They happen one after the other. And then what happens?
And then it starts again from the beginning. It continues the loop.
So why do we not see that here? You're showing me that your program ends here. When do I get to the end? What happens at the end here?
Oh, yeah, like once it becomes at end, it will not instruct any instructions again.
But do you have an end in your program, in your actual program?
No.
No. No, that's right. You don't, right? You have a loop function there because this is Arduino code. Okay.
Yes.
So again, this I would, I want to point out that this doing pseudocode is not just a whatever. It's actually, how do you design your code? Did you write your pseudocode before or after your program?
Actually, I write it before this flowchart.
So you wrote this before the project, before the program, but then how did you manage to write? Because your program should have been written following the guidelines of your pseudocode. So how did it end up that your program doesn't follow the sequence of events as in your pseudocode? Because if I were to follow this, let's say, even if I assume multi-threading here, basically what would happen is we would go through this and we would get stuck in one loop or another, to be honest. Okay, we get stuck in one loop or another. And because you're showing me here yes and you're showing me no, right? If you look at the diamond decision-making diamonds there, no is going back into, no should be coming out of these diamonds. It's right. So again, the flow here. So I find it very particular that you're saying you design your program via these decision-making process. Yes. And yet your program runs totally different than that. Okay, so again, that's unfortunately something you would have learned if you guys had a intro to programming course, and it shows a lot that that's that needs to be added to the alternate energy system. All right. Yeah. So yeah. All right. Could you bring up your block diagram for a second?
Sure. Here it is.
All right. Maybe I misunderstood. Okay, I'm asking for clarification on this one.
Yeah.
You explained the block diagram, and I kind of thought I was following along. I did, honestly. And then as you're going through, then you get to your demo, and your device has a float. Okay. Yeah. So where is the float here? Oh, it's right there. Sorry, float.
Yeah.
Geez. Okay. For whatever reason, I couldn't see it on there, and it was confusing me. Okay. Very well. Thank you.
Block, maybe it's.
Yeah, no, well, it is a small block, but it doesn't matter. I'm the one that obviously couldn't see it. I must have missed that part when you were explaining it in your block diagram, and then afterward, oh, well, I know why, because you have version 1.5, and you submitted us with version 1.4 here.
Yes,
that doesn't have the float switch. That's why.
Yes.
All right. Why didn't we get version 1.5?
Actually, at the very last moment, I was working on my PCB and to make this enclosure and everything, so I didn't get chance to edit this thing. So I did it in last moment. So
because there are substantial differences between the two. Oh my God, there are.
There is a big difference. Yeah.
Well, that's a big difference. No wonder. Again, to my confusion. Okay, well then the onus is on you on that part, not me. I thought I had made a mistake, but no, it just wasn't there. All right. Thank you. Well, it's all in the process of giving correct information, right? The handouts are important too, because I'm using the handouts to follow along with your presentation. So it's all right to have a handout that has a small alteration, but for me, this is a significant difference there. As I compare both of them, your drawing and my drawings are significantly different, right?
Yes.
All right. Anybody else have some questions there?
Is Mr. Roth, his question?
Yeah, you can hear me, right?
Yep.
Okay. Would we be able to, Kushal, visit your schematic, please?
Oh, yeah. There is.
I'd like you to, I'd like you to focus on, if you can bring us into with your pointer,
oh, yeah.
The relay coil part of the circuit. Yeah. But we can see that there.
I don't know.
Yeah. I'd like you to focus on the relay. You have your SPDT relay there. Yeah. So not on the contact part of the circuit, but on the coil part of that
this thing.
Relay. Yeah, that thing. Yeah. Can you explain to me? And actually, I think a good place to start here is, can you, with your pointer, draw the conventional current path that would exist there between the 5 volt, I think it's 5 volt, isn't it, up there? 5 volt supply.
Yeah, 5 volts, yes.
Yeah, the 5 volt supply, and then so I want you to show me the current path that occurs from the 5 volt supply and then through the relay coil to ground.
So like my 5 volts will come through this collector and of the transistor, and from the this is the 5 volt. Yes.
Does the 5 volts go anywhere?
There's 5 volts.
Yeah.
Yeah, it's coming directly from the this regulator IC output terminal.
Are you, before you go too far, are you sure it's the voltage that is going somewhere?
No, like I applied directly to the relay coil through this transistor.
Okay, so what is actually moving? Is it the voltage that's moving?
No, it's a current. Current is moving.
Right, it's
applying
charge
the voltage.
flow, right? Yeah. Okay.
Yes.
So trace for me the the current flow starting from the 5-volt supply down through the all the way through to ground through the relay
so like
coil.
My current will flow in this direction. Can you see my pointer actually?
Yes. Yep.
So my current will flow in this direction. It will go in here also, as well as it comes here from this coil, and it will ground here.
Yeah, it goes to ground on the left over there, right? Yeah. Okay.
Yes.
And so that occurs anytime that your sensor feeds sufficient base current, right, to the 2N2222.
Sorry, can you repeat it?
So,
this transistor. Yeah. Okay.
Right. Yeah. Okay. So what happens? So let's say that this has been on for a long period of time. You've got a constant current that is flowing through your transistor collector emitter junction. My question is, what happens as soon as the sensor detects that there is sufficient humidity in the soil? What happens next?
It will break the path. It will not let flow the current through this transistor to the relay coil and this LED too.
Okay. And how fast will the current go from its nominal value to 0? How quickly will that happen?
Like as I mentioned, like from peak value to normal value.
Yeah, so it's nominal current value. So whatever the nominal spec sheet current is for that coil, that relay coil. How quickly will the current drop from that nominal value down to 0?
Exactly, I don't know, but it's in fraction of second. Like maybe it's in millisecond.
Okay, so
it appears on the multimeter, and then it will it will reach to the 470 milliamps.
Okay, so you've said what I wanted to hear. It doesn't happen instantly or instantaneously. Why doesn't it happen instantaneously?
Like
why doesn't that current drop to 0 instantaneously?
Because like when I start the water pump, there is no water into the pipe, so it consumes more power to vacuum the water and through that whole pipe because of long pipe. And
oh yeah, okay, but we're talking about like the current here. Why doesn't the current drop to 0 instantly? And it has nothing to do with watering.
Well,
look at the circuit, right?
Yeah.
You traced me the current that flows from 5 volts down through. Why doesn't the current drop to 0 instantly?
Maybe because of this LED.
Well, that's not the current path that you traced for me, though, right? The current path that you traced for me went down through the coil, right?
Yes, but so it will becomes ground from this LED path as well. So.
Okay, but I don't want you to consider that part. I want you to consider the path that you traced for me.
Because of coil, like inductance.
Because of coil inductance, right?
Yeah.
So we have, when you combine the coil inductance and resistance and whatever other resistance is between 5 volts and ground in that path, you have an RL circuit there giving you a time constant, right?
Yes.
So now you can answer the question, right? How long does it take for the current to go to 0? In terms of time constants?
Like 5 tau?
5 time constants, right?
Yeah.
And it's practically 0. It still isn't quite 0, isn't it? After 5 time constants. Okay, so during those 5 time constants, what is happening? Because you've told me that the BJT collector emitter junction has opened, right?
Yes.
It is in cutoff. It's like an open switch, right?
Yes.
But you have told me that the current doesn't go to 0 right away. So
Yes.
how much? So what's going to happen across the collector emitter junction when it opens and the current doesn't quite go to zero right away? Is it going to be a very high resistance from collector to emitter when it goes to cutoff?
Actually, those diodes becomes as a reverse bias, so not we can say like it's a high resistance, but
well, it's like an open switch, right? It behaves
yes,
like an open switch, so it should be a very high resistance, right? Now it won't be the same as an open switch. We can read the data sheet on the 2N2222 to find out, but just without getting bogged down in those details, it looks like an open switch, so it's going to be a high resistance, right?
yeah.
So if the current doesn't go to zero right away, what is going to happen? Let's say the instant that the BJT goes to open condition to cutoff, right? What is going to happen to it? Because you still have nominal current flowing the instant that happens, the instant after that happens, because not even one time constant has passed yet, right? What are you going to get? What are you going to get across that collector emitter junction?
It's
in terms of voltage.
There's a like reverse voltage will be there.
Yes. Is it what? How high will it be? If you still have nominal current the moment after the switch opens, right? Essentially, you still have nominal current. How high is that voltage going to be?
It should be 5 volts, like reverse 5 volt.
You want to reconsider that answer?
Like whatever.
Let's throw some numbers in. What would be a typical resistance for an open switch? Just we don't care what kind of switch. We don't care if it's a BJT switch. If you open the switch, so maybe it's a megohm. Can we use 1 megohm as maybe 1 megahm's too low? I don't know. Maybe 10 megohms. But
10 megohms.
Okay, if you want to use 10 megohms, the math's still pretty easy on that. And what's the nominal? What's the nominal current for your relay coil?
So according to 10 megohm.
Just roughly, what would it be? Did you notice from your?
It's it's in microamps.
Is it microamps? Yeah, that's pretty low for a relay coil.
Like once it will cut the parts on that time.
What if it was even a milliamp or 10 milliamps or something? What if you ran the Ohm's law equation on that? Even at 10 milliamps, say, if it was 10 milliamps.
Yeah. So are you asking about the resistance?
Yeah. So if you multiply that 10 megohms times the 10 milliamps, what do you get for a voltage?
Yeah. Is it 10 milliamps, right?
Let's just say, 10 milliamps times the 10 megohms as an example. These are rough numbers. I mean, we could go figure out what they really are, but I want you to answer this quickly.
Ron, can you another minute? You'll have to wrap it up there. We're running out of time.
I know. I'd like you to answer the question though, because I want
100 kilo.
100 kilovolts, right?
Yeah.
Yeah. Okay. So, what's that going to do to your BJT if you have 100 kilovolts across the collector emitter? Yeah. What are you going to do to solve that problem? I'm expecting this is going to happen. Actually, it won't happen on the first few times. It'll probably happen on the 50th or the 100th time, and you'll wonder why the transistor burned out. Right.
So,
what can you do to prevent that?
Flyback power diode.
So you should install yes, exactly. You should have a freewheeling diode installed there. Okay. Where though? And maybe we don't have time. Maybe we're out of time.
It should be here across the relay coil.
Okay, so you want you want to provide an alternative path for that current so that it can just go in a loop exactly. Okay, so great. Thank you for answering that question. We're out of time.
Thank you.
All right. Thank you, Casal. Very good. Sometimes it takes a little while to get the answers, but we eventually get there, don't we? All right. So we'll take our. It's going to be a brief break this time around to 11:30 or 10:30. Sorry, my mistake. 10:30. That would have been a long break, actually. We'll go to 10:30, and then Alexei Burakov will come around and tell us about his project, the microcontroller regulated air heater. Okay, so join us in 7 minutes or so.
Thank you, everyone.
Thank you, Casal.
Alexei, we can see your screen. I think we cannot hear you if you're trying to speak.
Okay, thank you very much. No, I'm not trying to speak. I was just checking video.
Okay, I can see your screen right now.
Oh, okay, thank you very much.
No problem.
Okay, so welcome back. Very brief interval there. As instructors, we get kind of, I won't say carried away, but we get a little bit passionate about the questions and getting the students to answer the questions properly and that. So that's kind of what happened last round there. And the student did very well. He came up with the answer in the end. That's what counts. All right, so 10:30, presentation number 3 for the morning is Alexei Burakov, and he has developed a microcontroller regulated air heater, and he wants to talk to us all about his results. So Alexei, I believe you're ready to go.
Yes, thank you very much. And I would like to continue our senior project symposium. Today I'm gonna do presentation regarding my project. My name is Alexei Burakov. I'm an industrial option student, as it was said before. My project name is Microcontroller Regulated Air Heater, and my advisor is Mr. Matt Calfe. And I would like to thank him now because he gave me lots of valuable advices during this project. I would like also to thank all the teaching team of the NBCC. It was my previous education was in different domains, so I had to put some efforts, and I appreciate the help from the teaching staff. Thank you very much, and I would like to begin my presentation. If you have any question while I'll go, if you need a quick answer, I never mind if somebody stops me and asks a question, I'll try to answer it. And let's start. First of all, I would like to introduce the agenda of today's presentation. I'm gonna make a quick introduction of the project, what it all was about, why it was selected, and what is the purpose of it. I would like to give you a functional overview of the different parts of the project, how it works, what it's supposed to do, and how it's accomplished. And also, I would like to describe the key components that I've chosen, and I believe that was a right choice because the project worked eventually. I would like to talk about the code that runs the project, and I will draw the conclusion regarding how project is ready and what can be improved and what could be a follow-up. So the main task of the project, when I was thinking about it, was to create a device which is capable to maintain certain temperature, and also this task implies the next one, which I need something that takes heat from one space and send it to another, so basically equalizing the temperatures. Additional requirements I was keeping in mind when developing this project. I would like it to be grid independent, so it could potentially work during the power outages. And I would like it to be easily upgraded, so I could potentially deal with the higher loads, not only with the one I've chosen for this project, but also with the more powerful fans and devices and more powerful applications. As of today, I see 2 potential areas of application of this project. It could be solar air heaters, any models. Doesn't matter, it could be a solar wall, it could be any type of collector, because sometimes people use perforated metal sheets attached to the wall to collect heat energy from the sun. Some projects, some solar air heaters you can find in the internet are just standalone boxes with glazing and another type of metal absorber. But anyway, they do the same thing. They collect free energy from the sun, absorb it, and they can share this heat energy with the space selected. According to our textbook on solar energy, the heat output can be up to 500 watts per square meter in a sunny day, not in any day given. And That can be with the surface area is big enough and they are orientated well. They can bring substantial savings to the power bill and can provide some heat even during the power outages. Second potential application are the proofing chambers. I didn't put the picture of proofing chambers here just because I wasn't sure the pictures available on internet are free to use. But it's very simple device, widely used in the bread manufacturing industry. It's steam generator. Typically, it's a boiler that produces steam, hotter steam, and this steam is supplied into a room to be heated because temperature and the steam are the key parameters when you proof breads or baked goods in an industrial setting, because it saves time of the fermentation and it also saves space this way, because if you ferment faster, you need so much space. And I don't see my application to my device to be used in a large scale industrial application because they do distribution and humidity control pretty well, but it could be very good supplement to the small or medium sized proofing chambers, because they usually have only one steam generator located in one corner or even under the ceiling of the proofing chamber. It has only one fan, and it just what it does is just switching on, sending some steam, and it's not evenly distributed usually, especially if you fill this room with the products. There is a huge prevention for the airflow occurs, and also they usually those inexpensive and small-sized proofing chambers are usually installed directly on the tile floor, so there is considerable losses through the floor surface. And that usually results of temperature difference between top and bottom about 10 degrees or higher, and it definitely impacts the process and impacts the quality of ready products. So additional inexpensive system attached to this one would be very helpful, because steam generator is quite expensive product compared to this device, and buying a second steam generator doesn't usually make sense because you don't need excessive steam. Excessive steam is also not good for the quality. The key parameters that this system would use would be the set point, the temperature set point, the actual temperature readings that are supposed to be updated constantly and monitored, the difference of those readings between two spaces to be compared, and the speed of equalization. I mean, the larger is the difference, the faster is the heat to be supplied in the area to be heated. The key steps of this project, except of course voltage regulation, it's going to be discussed later. For the project itself, the key steps are the temperature measuring, temperature comparison. Comparison should be done with a set point again and between two different values. Calculation of temperature difference, decision and production of the output signal. The block diagram here represents the process that I discussed before, and it also represents some key components that you see here. It's a microcontroller, which basically takes decision. It's a temperature sensor that takes the readings. It's a voltage regulator that provides a stable level of voltage and reference voltage. And of course, the electronic switch and programmer which sends the code into the microcontroller. And I'll talk in more details about these components a bit later. So as you can see from the block diagram, there are two power supply. I did them intentionally, two different ones, so that could work independently, and I could adjust the voltage supply for the fan if I need to upgrade it. But now for this project, they are identical. There is 9-volt battery connected through the switch to the voltage regulator, and the voltage regulator outputs voltage. Voltage line 1, VCC1, supplies microcontroller and sensors, and the voltage line 2 supplies the fan via MOSFET switch when it's closed, of course. And there are two room temperatures that provide inputs. And based on those inputs, MCU compares one of them with the set point. Its temperature room sensor is being compared with a set point. And after that, those values can be updated and sent to the serial monitor if it's needed, if it's connected. Or they simply calculate the difference. And the difference is the factor that allows the microcontroller to choose the duty cycle. Output duty cycle signal is sent. It's the same signal sent to LED 3 so that people or operators could see what's going on, is when in operation or not, is the temperature difference detected or not, and also to send to MOSFET, which opens and closes depending on the duty cycle, providing the variation of speed for the fan. The schematic of this circuit is also presented here. This is the two power supplies. I included the fuse in both circuits, and fuse holder itself and all the circuit, all the traces of PCB, they can handle higher currents. So if you need to upgrade to more high application, you just need to replace the fuse, basically, and the circuit will operate exactly the same. And you don't need more than 5 volts for the microcontroller, so the first power line will stay the same regardless of which fan to be controlled. The key electronics components, what I see here, are the voltage regulator. I have chosen MCP1702 because it provided stable 5 volts if collected properly in accordance with data sheets. It has very low voltage dropout, so I really need 5.65 volts to get 5 volts output. And I checked my circuit working with different voltage level because I used power supply built during the first year lab. And it was working equally the same from 9 volts or 5.65. It still was operating under 5 volts, but probably because of reference voltage difference, the readings sent were not what I quite expected. But at the voltage is 5.65 and higher, it was working very, very well. I also have a TMP temperature sensor. This is the temperature sensor that we use widely in our labs, in our embedded course and before. And it's I've chosen modification which can be operatable at -42 plus 125 degrees Celsius, which is high range, and it's going to be sufficient range to operate either heater or either proofing chamber or even cold storage room. It will be doing the job quick enough and very reliably. I also presented here, this is of course the key part of the circuit, is the microcontroller at Mega 328P. That is a multifunctional microcontroller, widely used, inexpensive, and I was very happy to work with it. Another part is presented here, was very important, is a programmer. I use PickKit for programmer, and I had to learn how to work in MPLAB to use this programmer properly. But after I have learned, it proved to be very easy to work IDE, very reliable, and at the end of the day, I was happy that I was introduced to this program. It makes my life and other people's life much easier. And I also chose an electronic switch to control the load. I've chosen IRF Z48. It's not the MOSFET that we use in our labs, but I was looking for something as I said before, for the possibility to upgrade my application. And I was looking for the MOSFET which can run higher loads continuously without any complications. And first thing I checked, this is the images taken from datasheet of Atmega 328, and from the DG key, the key information about this MOSFET, I've checked voltage, different output voltages that can be output by Atmega chip at different temperatures. That was the key parameters for me, because area of installation can be different, and as well the temperature inside the enclosure can raise. And I realized that if I supply stable 5 volts, the voltage output will never be below 4.4 volts. So I was looking for a MOSFET, which logic level MOSFET, which can capable to switch reliably at voltages 4 volts and higher. This is what's happened. I also checked the datasheet for the minimal VGS that may potentially, under certain conditions, switch the MOSFET. And it used to be, I found out that it's 2 volts. And 2 volts was definitely higher than the V out low signal of the Atmega. That's why I thought that maybe that's a good choice. Another characteristic that I liked was that the continuous current is 64 amperes. That is much higher than I need for any application, so it should operate reliably without overheating. And I was expecting my circuit to work absolutely perfect after that, but I ran into unexpected problem. I must say that this resistor was in the circuit initially, but I saw it only just to allow minimum current from the output of Atmega 328P, and I decided that I need to make sure that the voltage at this point has maximum close value to 5 volts. So because with the small currents going through, the maximum voltage drop would occur here, and the maximum voltage at this point will be equal to the voltage at the gate. And I was surprised that initially my circuit wasn't operating very well, despite I was having 5 volts output. It wasn't switching on properly, and sometimes it wasn't switching off. After I've made some experiments, I've checked pinouts, and then I noticed that the MOSFET acts as a capacitor, and I recall the course from Mr. Boyk. He told very well on the desk about these parasitic capacitors, how they should be taken into consideration. And I realized maybe it was for purpose. And the problem was probably because initially my prototype circuit was assembled on 2 breadboards, and despite the grounds were connected in one spot, this was located on the other breadboard versus MOSFET, and it was probably not close enough to pull down the voltage after MOSFET was supposed to switch off. And that's why after I moved it directly across the gate and the source, the problem was solved, and the circuit started working as expected without any glitches or something. And after I solved the problem with my MOSFET, I reached my adaptability goals. It was capable to operate reliably from batteries or power supply. It was capable to operate at negative and positive temperatures, and it was capable to control different various loads. And now I would like to present the flowchart, because after the circuit was working as expected, the only things to take care was the code. And this is the flowchart of this program. After the start, 2 readings should be taken. They should be compared with each other, and one of them should be compared to the set point. If the set point is not what it should be, the temperature difference should be the difference in reading should be calculated, and this temperature difference, this value, is used to determine the duty cycle, to select duty cycle for the process. If it's equals 0, it's going back to recheck value, and so it's going in continuous short loop. If it's not, if it's above the 0, it should choose one of the mode. I'll later extend it to another couple more modes just to make larger variation of signal. And for the code, as I showed you on schematic, my two temperature sensors connected to ADC channel 0 and ADC channel 1 on port A of Atmega 328P. And the key thing for me was to make sure that there is, because basically there are 8 ADC channels on Atmega, but the microcontroller is capable to process only one at a time. So I needed a reliable switch between those ADC so that Atmega could take one reading and another. And this is the sample code for the reading from ADC 0, because I need to activate 4 MUX bit in AddMUX register, and I need to make sure for the ADC 0 they all have to be 0. That's why this is what this line of code is for. Then I start conversion. Then I wait until conversion is done, and then ADC value 0 is ready and it's saved to the memory. And it can be transmitted to the serial monitor if it's needed. After that, the same operation is repeated for ADC channel 1, is only exception that in this case, 1 should be written in MUX 0 because it's number. And after that, after I got to reading, ADC different. ADC value 1 is compared to the set point because it's a room temperature in my case, in this case. And ADC difference is calculated, and it's possible for the program to select duty cycle. The decision is made by assigning a value using a 16-bit register, and I've got 16-bit timer 1 in serving pins 15 and 16 on Atmega 328. That's why this value assigned could be between 0 and 65535. And the value assigned is basically the number of counts done by the controlling counter. And once this value is reached, the output goes to low. Before that, until the value is below the number of counts is below the value assigned, the output stays high. And that happens every period while in operation. And high-low signal means that the fan is either on and off. It's just high signal means that the voltage is over 5 volts, MOSFET is switching on. If it's below 4 volts, it's switching off. And here is the representation of duty cycle, but I believe everyone in this room knows what is that. It's just time on versus period of time. Another important component that I don't use constantly, but they are needed from time to time, is FTDI. I use CH340 to connect it as FTDI, so I just connected 4 pins of it. Receive, transmit, VCC and ground, NP kit for programming for Atmega 328P. Very convenient application created by the MP Lab. It was very easy to work compared to what we've tried before. I was hesitating about using it, but after I made some effort, it was much easier and big deal. As a conclusion of this presentation, I would like to say that this product was checked before the assembly. I have to build 2 prototypes just for the case to check that it's working. It was checked after the assembly into PCB after soldering, and it was evaluated with advisor. It's doing this key task properly, and as a follow-up or improvement, I would think about the cable, because when I was connecting the cable to between the heater and this block, I had to use special connect splices to reduce the pressure on these terminal blocks. As well, I would maybe think about design of the heater that I built for the testing. It's definitely working, but because I built a small one, and even the small fan that I used for the test was drawing all the available hot air within 1 minute. That's not enough, definitely. If I plan to use it practically, that's what I'm going to use. So I need to build a bigger one and maybe choose a better space for the installation, because I use space located under the overhang. It's safer during the snow time. But it's not optimal because there is no maximal exposure to the sun. But if regarding the electronic part of the circuit, it was working as it was expected, and I was very happy about that. This is the sources that I used for my final report and for this presentation. It's our textbooks mainly, it's some internet resources, and of course it's a data sheets from Infineon, Microchip, and other suppliers of the components. I would like to thank you for your time, for your attention, and if you don't mind, I would start the demonstration now. By the way, is video okay? Can you hear and listen to me? Because I don't see much feedback.
Yeah, we hear you fine.
Okay. Do you see it well enough now? I mean, fan and the control.
Yeah, you could maybe back out a little bit.
Closer?
No, move your camera back away. Farther away.
Back here. Okay. So this is the control block. I've brought it from downstairs. I connected it just to the breadboard for the outside heat sensor. This is the fan. Now the temperature is the room. I need to check it. Now they're both, it's just slightly above the set point. Now it's okay. Oh no, it's below. It should be working okay. So basically what I see, I switch power supply for the circuit itself. This is the power supply for the fan. And now they are equalized, so there is no motion, there is no need to deliver from one room to another. But if I hit it a little bit, it should start working. While it's working, it demonstrated the duty cycle. And as well, current duty cycle. As long as they hit and the logic is different, it will switch to 100% duty cycle eventually. And this heater will be constantly on. I mean, the red LED will be constantly on. I probably cannot get enough temperature difference now with my finger, so I'll try to use heater. So duty cycle increased, the fan speed has increased. Now it's cooling down again, so the duty cycle drops. And it can be seen by the red LED, but I'll try to heat up the room temperature sensor faster, so it will stop completely. because after equalization they should stop. Maybe I'll have to use fan again. Now they're equal, or they were equal for a short period of time, and they have stopped. I'll try to hit it with my, oh, it's not enough temperature. So I hit it again with the fan, so it stopped. As you can see, after I remove heat, it starts working again because the first one was properly heated. And that was all for the presentation. Thanks for your attention, and I can take questions now.
Okay, I got a quick one, if you don't mind, Alexei. Now, I think I may have missed something. You showed that you have two separate power supplies, one for your control circuit, one for your fan.
Yes.
I believe I must have missed. Why did you feel that was necessary? Is that something you discovered once you were building, or was that a starting assumption?
Actually, if I decide to keep this fan forever for this application, I would be good with the one battery probably. But I was looking for the possibility potentially to control higher loads with this application.
Oh, okay, I got you. I think you did say that. Now you mentioned it. Sorry.
So, but basically, when I was experimenting, I either used one battery for both of them at the beginning, or power supply set to 565 volts.
Right.
But potentially, that's basically why I chosen this larger MOSFET, more powerful MOSFET, so that it could handle higher loads potentially.
Exactly. Thank you.
You're welcome.
In your flow chart, you showed both in the fan control and the, I guess, the temperature comparator circuit, you showed delay blocks. And I think in the code, you showed that how the amount of delay was determined. Why was the delay necessary?
At the beginning, I was planning to stipulate certain delays because I was afraid that it will be very quick switching and the readings will be confused. But after that, after I put the old code together, I realized that it's working without interruptions and confusion, so delay basically were not needed. So
yeah, as the T1, T2 comparison fluctuated around zero, you were concerned with switching noise, and that's what it was?
Initially, I was thinking that maybe I will not be able to switch the MOSFET instantly, so I was giving it some time to finish the operation, and after that, to resume to new mode. But
and you did explain 65,500 and something 36 cycles of delay. How was your amount of delay determined? Was that hard coded? I missed it. I don't read code. Sorry.
Okay. Just give me a second. This value, which I assign for each duty cycle, is saved to the output compare register, and this value is compared to the maximum count for one period of time, which is 60 for 16-bit timer. It's 65.3.5. Basically, no, it's 65.3.536 because you start counting from 0. So I just put this value in between For the 100% duty cycle, I need to put 65,535, and all the counts will be counted as a high.
Thank you.
Because I'm using non-inverted mode, that's why the output stays high as long as the number of count is below the top level I set.
Okay, thank you.
You're welcome.
Okay, I guess I can chime in there with a question.
Okay.
So your project title is a microcontroller regulated air heater.
Yes.
Is there a heating element within your project?
I built one for the testing. It was basically the same heater that you can see on YouTube. It was a wooden frame with a fan inside on top level and with air grill underneath to collect the air. And I've painted downspouts, but because it was a small project just to test, it was a downspouts extension. They're like 40 centimeters long. I put it in and I attempted when I was a sunny day, it not so many. Yeah, it was collecting. It was capable at the peak time to collect up to reach up to like 60 degrees Celsius inside.
Okay.
And after that, for the demonstrations, I just removed the fan from outside, from inside, and that's it. But anyway, the small one which I used, I did the same one as for the concept drawing. It's too small to produce enough heat. So even in a sunny day, I would expect it to be maximum capacity to produce enough, little bit enough heat for the working space in the basement, but not enough to heat the basement itself.
So your project takes solar heat as a heating source, essentially?
Essentially, yes. But I was thinking how else it could be implemented. But initial idea was, yes, to build a solar heater and something that regulates the supply. So that people would not have to switch on, switch off, checking is the hot air available or not, or just let it go. When it's available, it's on. It's not available, it's off.
So your project is not in fact a heater, it's more of a regulator for a heat source, essentially?
It's more like microcontroller.
Right. Well, it's run by a microcontroller, yes.
Yes.
But it's not a heating source, but it regulates solar heat, distributes it within the room, essentially.
Yes.
So maybe a regulator, a heater regulator might have been a better title for your project.
Yes, you're probably right. Because it might be confusing. People may expect something large and hot, but it's just
it's just yeah, no, that's fine. Okay, thanks.
Thank you.
Alexei, can you bring up your schematic? And just while we're waiting for that, I think I want to kind of reflect Denis' concern that when you were explaining, I don't think it was very clear as to what the device was regulating. Okay, it's like how the heater element. You should have shown maybe a setup of the PV concept. In fact, in your demo, I think that would have served you better too than just the fan. All right, or at least show it so that people saw what it was, and then run the fan independently. So
okay.
All right. I want you one comment that I was talking to the instructors this morning, and one comment that I pointed out was in many of the MCU based products or projects, the microcontroller projects, there seems to have been a lack of a certain component present in the design, and in your case it is there. Could you tell me what is the purpose of C9 and why you chose to include that in your design?
The purpose of
the capacitor C9?
Okay. It's stabilized voltage. It's basically the C9 is connected to the between 0.7 and 8, and
which are what?
It's a VCC, basically, and ground of the Atmega 328P. Okay. And the same capacitor is required at the voltage reference. It stabilizes voltage supplies and removes the voltage spikes. So it's constantly 5 volts, not like 4.5 or.
So what would cause the variation in voltage on your supply line?
In my voltage supply line, it would be caused by output of the regulator, but I also have this capacitor at the output of the voltage regulator. It just
no, the voltage regulator should be able to, on average, supply you with the voltage you want. That's the design of it, right? But it's good. Well, first of all, what's the name of this capacitor? What do we call these capacitors?
Decoupling.
Decoupling capacitors, right? And it's good practice whenever you are using digital systems to use a lot of decoupling capacitors. All your silicone should be using decoupling capacitors. So what would be, in this case, you chose to put one correctly between VCC and ground, okay? And you're saying, well, it's in case the voltage goes down, but how is it? What would be the cause of this variation in voltage?
The variation in voltage could be, say, I connect FTDI for a moment, and it can cause either voltage spikes because it's connected to computer, or drop of the voltage.
What else? What else? You have them on TMP36. Also, right? You'll notice
yes.
I noticed you have them there too, which is a good practice too. So what else could cause variations?
Basically, TMP36 also need 5 volts, and when in operation, they also can drain some current, and it may also.
Where do they physically have to be? Can we all just lump those near the voltage regulators, or where do they physically, where did you have to locate these?
We physically should locate them closer. One of them should be closer to output if you talk about temperature sensor, because it stabilizes the output.
Not the output, no. You don't have them located at the output.
And also closer to input, because it keeps the supply stable.
The supply, not the input, the supply, right? You have to have them physically as near to the pins, the supply and ground pins as possible, okay? Yes. To prevent what we call transients, okay? To prevent transients, yes. All right? So what happens is other devices in your circuit, when they switch, the power supply can't necessarily react quickly. For example, your Q1 there, when it starts switching, okay, yes. and it's pulling on VCC2, it may not be able to, the VCC2 may not be able to supply the current demand instantaneously because of inductive nature of the traces and so on. And also, Q1 tends to be capacitive in nature itself, so it'll store energy and release it back in. So that causes the power supply to vary. Not necessarily the power supply itself, but near the ICs, they're being fed by possibly the same supply. So we want to eliminate these transients and make sure that these very fast changing, brief, instant pulses don't affect your IC. For example, if IC1 there were to go low enough, it'll brown out, right? It'll go into brown out protection mode, and then it won't be working. Okay, so we try to attenuate all these signals or this noise. I guess it's not signals, it's noise at this point near VCC and ground. So anybody that uses an MCU or any kind of silicone when you're feeding the VCC, decoupling capacitors are a must. Okay, they're a must for that. So anyways, I'll let the floor to other people. Anybody else want to?
Thank you.
No problem. I have Don or Denis. I have a minor issue I got to deal with in a test I'm supervising. Can you guys kind of take over for the next few minutes there? I'll be back.
Sure, no problem.
I think we're probably, I guess, we have 4 minutes if there's any other questions.
Yeah.
My main questions were answered already. It had to do with the multiple batteries and the title, essentially. Ron, are you good with your? You don't have any other questions?
Yeah, I think that's good. We're really up against the time limit here, anyway. So.
Yeah. All right. Well, we'll leave it at that. Good job, Alexei.
Thank you very much. Thank you.
So thanks, we'll take a quick break here, and we'll have another presentation at 11:30. Who is Brandon Ryan, who's going to present at 11:30. So we'll take a quick break, and we'll attend his presentation at 11:30. All right. See you soon.
Yes, camera is good. It's just your face maybe load the presentation now, because for mine it took like a few minutes to load. What I noticed.
All right, we should all be back from break now. So we'll carry on with the presentations now with Brandon Ryan, who's doing his presentation on ECG units. So you can go ahead when you're ready, Brandon.
All right. One second here. Is that showing up all right?
Yeah, we can see that.
Okay, cool. Hey everyone, my name is Brandon. I'm in the industrial controls option, and today I'm going to be talking about my attempt at a ECG unit. And in this presentation, I plan on going over just my intent and motivation behind specifically why I chose to build an ECG. Also include a brief overview of ECG technology, just so everyone's up to speed and everyone's on the same page. We'll also be going over the project documents and breaking them down in a technical manner to understand more about the functionality of the project. And then we'll have a quick look at the final status of the project. So starting off, we're just going to have a quick look at ECG technology. We're going to go over the definition, what a bipolar configuration is, what exactly an Einthoven's triangle is, and certain cardiac waveform landmarks that also include certain pathologies and certain causes behind aberrations. And start with the definition here. So an ECG, or sometimes known as an EKG, is an echocardiogram, and essentially it's just a measurement of, or device which measures electrical activity in the heart. And often the two terms are used interchangeably to describe both the produced waveform and the device itself. But for this presentation, when I say ECG in and of itself, I am referring to the device. When I am referring to an ECG waveform, I'm referring to the waveform, just to clarify. So ECGs generally include some form of plotting or graphing. As we look in the next figure here, we can see one that includes two separate types of graphing, including a paper output and a digital display. These aren't commonly found very often now, but in some underdeveloped countries, this is used pretty commonly. The version of an ECG you're probably more familiar with is the standard digital ECG. You can see these in hospitals. I'm sure you've seen them in hospital dramas or TV shows. It's the standard machine that goes beep. So a bipolar configuration. So how exactly an ECG receives data from the heart is through a series of electrodes. And if we go back here, one second here, if we go back to the digital ECG, it usually has a 12-lead configuration. So 12 separate electrodes are placed along the body in specific places to give a better picture of the activity in the heart. However, it is possible to use just a bipolar configuration. So bipolar in this sense means that only two of the electrodes are actually used to take measurements. The third one is used as a reference point for the other two. Another thing to note is that the term lead does not mean electrode. This was very confusing when I started researching this topic, but the electrode is the actual tab that they put on your body. A lead is the connection. So say I have two electrodes right here and here. The lead is the connection that's formed between the two electrodes, just so everyone is aware of that. So AVR, AVL, and AVF. What those mean are right arm electrode, left arm electrode, and left leg electrode. I'm not actually certain why it's called AVF. I never found that in all my time researching it, but the purpose of these three electrodes is to measure the heart at three separate axes. So the right lead measures at a angle of 150 degrees. Left arm electrode measures at -30, and left leg measures at 90 degrees respectively. I'll go in the next figure. In the second figure, I will explain in more detail what those degrees actually mean and try to help everyone visualize that. This presentation is limited, however. I am not a medical professional. I have absolutely zero training, and before this project, I had zero background or idea of any of these terms. So we will not be dealing with anterior, posterior, superior, inferior vectors and different methods and modes of measuring the heart, but not for the sake of it going over the audience or your guys' heads, but for the sake of it going over mine. So describing the placement of a bipolar configuration, there's a reason why I specifically chose these 2 points. So the 3 points, even though the left leg electrode is called a left leg electrode, its entire purpose is just to be aligned on that axis with the leg. So it doesn't actually have to be placed directly on the left leg. It can be in some circumstances though. So by placing specific electrodes here, with the left leg acting as the reference, the left arm acting as positive, I believe, and right arm acting as negative, you get a clearer picture, and next slide shows this. You get this, and what this is called in the medical community is an Einthoven's triangle. And so the idea is that you're trying to measure the electrical activity of the heart from 3 specific angles. And when you do that, you form a triangle with the leads, which each one is centered around a specific area of the heart where electrical activity should be recorded. So going back a couple slides, I mentioned the axes. I mentioned the specific angles. What that entails is if you imagine a circle being drawn. 1 second here. Oh, sorry. If you imagine a circle, and this is not going to be a great circle, if you imagine a circle being drawn around here, centered around the heart, and you look at these angles, so if we start drawing angles like here, 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 at specific points, what these angles line up to, essentially, if we call this 0 degrees, this one would be -30 degrees. This one would be 90 degrees. And this one would be 150 degrees, I believe. Yeah. The purpose of the circle isn't really, the knowledge of the circle isn't required to understand bipolar configurations, but it is important, and I'll clear all that junk up here. It is important for understanding more powerful ECG units, such as the ones commonly found in hospitals, where instead of forming just a triangle, you are forming a circle with 12 points of measurement, essentially. So moving on here, cardiac waveform landmarks. So probably should have put this first. This is a typical ECG signal. Consists of 4 main parts, essentially. The P wave, the QRS complex, the ST segment, and the T wave. There is another portion that I'll mention in the previous slide. So when analyzing an ECG waveform, there are many signs, many tells, which a trained professional can look at to determine what might be specifically ailing your heart. So for a P wave, duration greater than 80 seconds indicates some form of atrial enlargement. So if it's a right atrial enlargement, it causes a taller wave greater than the nominal 0.25 millivolts. And this atrium, I believe, deals with venous circulation. So circulation of the blood flowing through the veins. Left atrial enlargement causes the P wave to have a split down the middle and causes a little ripple. The left atrium primarily deals with pulmonary circulation, so that of the lungs. The QRS complex, if it lasts more than 100 milliseconds, indicates hypokalemia, which is essentially just a lack of potassium. The ST segment, depression of the segment. So depression essentially means the ST segment is meant to rest at 0, at a potential of 0 volts. If it is depressed, it's significantly below that. And the depression of this segment indicates myocardial ischemia, which is a constriction of blood flow to certain limbs or extremities, and also is in conjunction with hypoxia, which is a lack of oxygen to the limbs. Remember this one, because this will be coming up later. Finally, the U wave. So if we go forward, you'll notice that the U wave isn't on this diagram. And that's because the U wave generally doesn't show up in a normal resting heartbeat. U wave only generally shows up after a long period of intense exercise. I believe typically it's about an hour and a half before it can be properly registered. But if the U wave can, one thing I should probably add about the U wave is that as of right now, there are only hypotheses as to what causes the U wave, but there's no specific function that anyone's been able to pin down which causes it in the first place. So if a U wave is present in a resting heartbeat, that generally indicates hypokalemia, hypercalcemia, or hyperthyroidism. Hypokalemia, similar to QRS complex, just means a lack of potassium. Hypercalcemia is a excessive amount of calcium in the body. And hyperthyroidism means a overproduction of a hormone called thyroxine, which governs digestion, muscle health, and responsiveness and bone maintenance. And I wanted to break this down a bit and go into detail on these specific pathologies, because when I first started this project, I didn't know anything about ECGs. And to be honest, I always generally thought of them as glorified heartbeat monitors. I never really understood the utility or usefulness of such a machine. And I think maybe it's just me, but I think many people also may have the same impression. And so it's useful to understand that there is more than just the monitoring of a heartbeat. You can make general determinations about someone's overall health from a ECG waveform. So the project documents. Start with the conceptual drawing. My idea behind the project was to create a more cost-effective version of a pre-existing medical instrument, which could be used for personal use. More often than not, third-party ECGs can be bought. However, the prices can be extreme at best. So what I wanted to do was create a very bare-bones, stripped-down build, which maintained a comparable level of performance to ECGs found in hospitals. So analyzing the diagram here, I'm not sure how zoomed in that is on your guys' end, but I'm going to zoom in anyway. I opted for a very simplistic user interface. Only 2 specific points were given, which allowed the user to interact with the device. That was the power switch and a CMRR adjustment potentiometer, and that will be explained in more detail in the schematic. Two methods of user indication were provided, or intended to be provided. First one was just a simple power LED, turned on when you turned on the device. Second was a pulse LED, and this would activate whenever, the QRS complex was seen by the device. And I'll go into more detail again in the schematic as to how I intended to achieve this. So for the front, fairly simple. I just had a 3.5 millimeter jack attached for the inputs. So the inputs, if I can untangle them here, the inputs would essentially be these three electrodes. Hopefully you guys can see them. These three electrodes corresponding to left arm, right arm, and left leg, respectively, which were connected to this 3.5 millimeter cable. And so for the back of the enclosure, I also had the output jack. And so my ECG unit, in and of itself, does not contain any sort of graphing method. However, the idea was to transmit the data, the output signal from the device to a computer, to where it could be processed by a third-party software, which analyzed the data coming into the sound card and then was able to plot it. I'll go into more detail towards the end of the presentation as to why this never happened. So moving on to the block diagram, I believe it's helpful if we divide this up into sections here. So if we move in here, oh, I can't draw. Okay, maybe we can just use this. So we'll start with the top here. So this is the power and reference stage. This is where the device is powered and the reference voltage for the instrumentation amplifiers was set. Power was delivered through 3 AAA batteries in series. This voltage was used to power the power indicator LED. Also provide the supply voltage for multiple components and dividers later on, and also serve to create the reference voltage, which was set to half the input, so 2.25 volts. The way this is set, specifically the electronics behind it, I'll jump into in the schematic in the next slide. So that clears up the power and reference. Talking about the inputs for a second here. So this is where the 3 electrodes came in. You'll notice that sensor 3 is called ground, and this is not specifically true. It's more common, or a voltage, or VREF, than it is ground. This is due to a electrical circuit called a right leg driver, which I'll again get into more detail later. But you have your positive input voltage, your negative input voltage. They were set into a low pass filter. This signal was then sent to the instrumentation amplifier, where it would be boosted. The intended gain of the system was around 2000, because the typical voltage at the surface of the skin, when measured by an electrode, is anywhere from microvolts to 5 millivolts at the most. It's a very small voltage and requires a very high level of amplification, and also requires a very high level of common mode rejection. So that's where the input low pass filter also comes into play in rejecting 60 hertz noise. For the comparator, so this is what governs the pulse indicator LED. A voltage divider was set, and once that threshold was surpassed by the output signal, it triggered a red LED to indicate a pulse. Fairly straightforward. And then you have the output low pass filter and then the output signal sent to a computer. So for the schematic, probably best if we start here, the power. So fairly straightforward. This was a schematic for the power indicator LED, two decoupling caps, or sorry, bypass capacitors, I believe, and then the output, or sorry, the supply voltage. The supply voltage was used here in this voltage divider to set it to approximately half the input. This comparator was set as a voltage follower to always output this halved input voltage. For the input, I had two capacitors which were set to essentially AC couple the input, because there's a very interesting effect that happens with electrodes on the skin. The human skin actually has a lot of acid on the surface, and so the application of an electrode creates almost a miniature battery, and this can create a DC offset in your input and can actually just completely swamp your input signal because it's so faint. So to rectify this, we got rid of all DC offsets at the input through these caps. Input buffer resistors. These resistors in parallel with this, the impedances of these two resistors in parallel combined with this capacitor created the values for the input low pass filter. Input low pass was set to below 50. As to why I didn't set it to 55, because the goal mainly was to get rid of 60 hertz noise. But I also figured in other countries such as Europe and Asia, the standard is 50 hertz. So aiming below 50 hertz would allow the device a little more flexibility in where it was implemented. So now we get to this stage here. This is the dual op-amp instrumentation amplifier setup. So a common instrumentation amplifier setup requires 3 op-amps, 2 as buffer inputs and 1 as the actual differential amplifier. There is a topology, however, that allows you to just use 2, which are essentially both set as differentials. In this case, to avoid having to use a negative supply requiring a second supply or input to power the op-amps, each op-amp was referenced to ground. This just saved me a whole lot of hassle. The resistor network here is the standard configuration for a dual op-amp instrumentation amplifier. So you have R8 acting as both a feedback resistor for U1A and also as a another resistor in the path of pin 13 from the output of pin 1. The gain potentiometer. The gain potentiometer is how I adjust the amplification of the signal. The specific reason why I require R7 in this network here is because the formula which governs gain in a dual op-amp configuration or dual op-amp in-amp configuration is when the gain potentiometer is set to a value close to 0, gain completely skyrockets. It gets close to dividing by 0, which approaches infinity. So by setting R7, we can limit the maximum allowable gain of the system. This here, R10, this balances the divider networks of R4 and R2. And while those two resistors are 1% tolerance, even a 1% tolerance can create a massive drop in CMRR of the system. So it's imperative that you balance it just right. And so a potentiometer was used to adjust this. And this was the potentiometer that was accessible at the top of the case. So with this, U1C here acts as the voltage reference output. This is attached to both the output and the input. For the output, it's attached that way because the output signal needs to be able to float at the level of the display device. And in order to do that without a, in order to be able to produce negative voltages without a negative supply, there needs to be a DC offset implemented to allow the output to dip below what would be considered the 0 or reference. I think also we can go over the pulse LED circuit, which actually is pretty straightforward. Buffer input from the output signal, input attached here, op amps configured in a syncing configuration as a comparator. So when the voltage that's set by this potentiometer, once this voltage exceeds this voltage, this triggers and current is sunk from the input and turns on the diode. Due to time, I think I'm actually going to skip the prototype, but I will talk about the prototype waveform. The prototype waveform, you might notice that this is not the oscilloscope screens from the lab. This is actually captured by a classmate of mine who very thankfully let me borrow his handheld oscilloscope, which lacked the power and adequacy of the normal senior labs. So this is why you see a lot of noise. So delving into this real quick, we can actually see here this little dip which occurs at each cycle. That is the Q point. Very identifiably, we can also notice the QRS complex spike. We can also see here, I believe, from my best knowledge, this is actually the T wave. It's just very difficult to see because normally T waves are very low amplitude, and the amount of noise that was in the system just completely swamped the signal. You'll also notice that 0 is actually set right here. And if you remember me talking about the ST junction, that a depressed signal indicates some form of myocardial ischemia. Well, this is my waveform, and this actually makes sense because I've noticed recently that I've had multiple times where I'm sitting too long, maybe pulling an all-nighter, and the tips of my fingers or the tips of my toes or feet will turn purple due to a lack of oxygen flowing to the limbs. And so this was actually really good to see because it showed that even with a less capable oscilloscope, my device was still outputting a correct signal and one that I could verify myself. Moving on here. You might be noticing the way I've been talking about the project, intend to, or the way I intended to do things, because the project didn't work. I tried to build it, didn't work. Spent all night working on it before the functionality assessment. Nothing happened. So we'll quickly go over an autopsy and what great lengths I took to try and revive it. And also we'll talk about the issues faced and what went wrong. So the final circuit here looks fairly innocuous. I actually have it right here. This battery pack has a power switch actually built in, and you can see it's currently, or I don't know if you can see, but it is currently in the off position. And if I switch it on, nothing happens. Not even the power LED. I couldn't even get that. There was a point during the construction process where heartbeat and power were working as intended. However, some unknown issue caused the whole circuit to break. And I'll talk about what I believe those issues to be later on. Here's the bottom view for anyone who is interested. The enclosure. I did not have the screws and standoffs and bolts ordered for my case. So I went out of my way, or sorry, in an act of desperation, I essentially screwed a column of standoffs to act as screws and to space the board from the enclosure. And if we go to the next slide, because I didn't have any bolts that would match these, I actually sanded standoffs to fit onto the enclosure to mimic a bolt. I was very desperate, very rushed. It's quite unfortunate, honestly. So what could have gone wrong? Mistakes in the soldering process. I used a very low heat for my soldering iron, 320 degrees Celsius, my normal temperature. However, I did notice that it took longer to apply the solder, and by applying the iron for a longer period of time, it could have caused the pads on the board to peel, which it happened. And I went through great lengths to try and repair this, and at one point I did have them repaired. However, it is undoubtable that mistakes during the soldering process led to some form of circuit failure. Broken traces or connections. The PCB, once it was constructed and handed to me, I didn't notice any connectivity issues. However, during the process of construction, traces could have been nicked. In fact, certain traces were nicked and had to be replaced with complete solder. Had to be replaced with solder going between certain components. And also PCB design shortcomings. I was unfortunately very, very short for time during the PCB design phase. And so even though I obeyed all the CSR guidelines and had all my traces and signals connected, there could have been some unknown issue that slipped by me. So it doesn't work. What do I do now? There isn't much to talk about, but there isn't much to talk about in the way of project functionality. In fact, there's nothing to talk about in the way of project functionality. But it's not all doom and gloom. I've actually learned quite a lot during the research and development phase for this project, and I'm super excited, actually. I'm actually super excited to deliver this presentation because I find these sorts of medical devices and medical concepts really fascinating, and I hope you guys do as well. Hopefully, I haven't been rushed too fast here. During the course of this project, I have developed a better understanding of how to.
Brandon, you have 30 seconds. All right.
All right. Understood. So how to dive into relatively complex subjects with no prior background, and most importantly, the virtue of time management. In terms of the project being completed, it is unlikely. However, I do have access to external ways to manufacture PCB, so it is possible. Here are the references that I've gathered, and I'd like to thank everyone for their time. And this is probably a good time to start the questions.
Okay, thank you, Brandon, for actually a great presentation. I unfortunately didn't catch the whole thing. I'll just watch it on the recorded stream later on there. But from what I saw, it was a very informative presentation. I did see, though, just for your information, AVR, AVL, AVF. So A is augmented, V is voltage, right, left. And so it's right arm, left arm, and what do you think the F is? What other limbs are there left? You had the two arms covered, then what? Foot. There you go. And I will agree, it was actually hard to find. I was kind of looking for it there, and it was hard to find. Anyways, I just thought I'd let you in on that, which is, it's always good to try to.
Thank you.
Yeah, by all means. All right. Does anybody have some questions there? You can bring up the schematic for me if nobody wants to.
Yeah, 1 second. It's just because I want to be able to see you guys and present at the same time, but 1 second, I actually know how to do this. Okay. Oh, that's going to take a while to upload. You guys should have the schematic in the drawings package though, right?
Yeah, I think it's good for the whole for the whole, all your presenters to be able to see what we're talking about.
Sorry, it's taking a while to upload. I might just share my screen here.
There was a term you used, though. Oh,
which one?
You did use a term, though, while we're waiting. You used the term, your friend's oscillator lacked the power. What did you mean by that? Because I was confused. I was like, what? We don't usually reference in this oscillator with power, oscilloscope, sorry, not oscillator, oscilloscope with power. What did you?
Are you talking about at this point with the
ECG? At this point here, and again, I'm kind of quoting, kind of paraphrasing. You said your friend's oscilloscope lacked the power.
Capability. Okay. It wasn't powered. It was just clearly a handheld, miniaturized oscilloscope isn't going to have the same quality and resolution that the secret lab.
That's fine. I just wanted a little bit of clarification on that, on terminology, right? It's important to use proper terminology. All right. Yeah. If you could bring back the schematic there.
Is that readable?
You forgot to point out, too, I saw your breadboard go by. You forgot to point out to your audience that the breadboard did work. Your prototype did work on a breadboard level. It's unfortunate that it didn't work at the final product level, right? So
and during the PCB design process, even though I was rushed, I tried to follow as many of the same.
Yep, that's fine. But obviously, something came back to haunt you. Yeah, this did work though. All right, bring your schematic up for a second. I've got a couple of questions on that, and then I'll cede the floor to other evaluators. Curiosity here, C2, C1. What's the purpose of these two capacitors?
Yeah. Okay. So this during the early stages of this project, I followed a build guide fairly stringently and without really thinking. However, I did more research into why this might be necessary. So it turns out it's common practice for some devices to use a electrolytic and a ceramic in parallel, because the ceramic provides you with a higher level capacitance, but has very poor frequency responses at higher frequencies. It has higher levels of ESR and ESL. The ceramics have lower, and as such act as bypass capacitors. However, with a DC power supply, I don't think this was necessary. Maybe
actually, don't use the words "don't think." I think you should just say it wasn't necessary, right?
Okay, it was not necessary.
No, that type of configuration is based on having some kind of DC supply that has ripple, all right, on it, or something like that. Which in your case, the battery will never supply anything like that. Okay.
Okay.
All right. That's a good answer. I'm glad you were able to realize that. Where is it? In your, I guess it's in the block diagram.
Okay.
You said sensor 3. First of all, sensor 1, sensor 2, sensor 3 by all means should have been labeled AVL, AVR, F, right? I mean, that's what the users will know it by, okay? And you mentioned that sensor 3, and it's marked there as ground, but you said it's not ground.
Yeah.
Okay. So why would you call it ground then?
Because ground, by the definition that I'm familiar with, implies a potential of 0 volts. However, in this case, this was not used as a normal ground. This was used as reference. And
so why not call it reference then?
I'm not sure. I believe actually this was an update off of your feedback.
I don't think so.
I am confident. I believe I usually would have stated that as feedback.
Let's go look at your schematic for a second then, because that's why I'm not really sure that that's true, because show me the ground on that lead on your schematic.
The ground on that lead. Ground never actually comes in contact with that. So this this bottom, I don't know if you can see my mouse here.
Not at the moment. No, I don't know.
I've never used this, so I don't know how to insert my mouse to point. But I can't even really see it. The lower connection on J1 on the left side of the schematic, that is VREF. That's the common electrode. And you'll notice the
common. Okay, hold on. It's the common electrode, so it would be AVF.
AVF. Yes.
Okay.
Yeah.
Okay. And where does it go to ground?
It doesn't. It never touches ground.
There you go. Where is ground?
Ground is a rail or a connection between the battery and the.
There you go.
The
so that's why I'm pointing to your block diagram, saying obviously that's faulty there.
Yeah.
Because I can see clearly here that it's not. In fact, if anything, if you grounded that, this would not work. Okay.
Yeah, absolutely.
Now, my next question on that, when I follow that input and I go all the way across and I go to the other side, J2, I think your original intention here was this was going to be fed into an audio input of a computer so you could display it on a computer. Why would this not work?
This configuration with Jack 2 on the schematic?
Yeah.
I believe it has something to do with the voltage VREF connection should have been on the top connector of J2.
And I'm sure I pointed that out to you several times.
Yeah, I just wasn't confident because I kept looking up the how 3.5 millimeter jacks were structured, and I couldn't find anything conclusive as to how to run 2 signals on a 3 signal jack.
Oh, you should have come and seen me then, my friend. There's tons of resources there on that. Okay. I should have come and see me on that. All right. That's all the questions I have. If anybody else wants to pick up on this. Don, Denis?
A quick one, and maybe it's inappropriate in this sort of with no ground in your control circuit. Would it still not be useful to have some decoupling at your MCP 6024 power and ground leads? That'll help suppress any noise. I guess what would you decouple to? And Mr. Metcalf can help us with that.
So for decoupling the IC itself, when I was looking up, so you're talking about the power.
Definitely, that should have been decoupled by all means.
Should have been.
Sorry about that.
Okay. I was under the impression that decoupling caps were mainly used for ICs. They were mainly used in higher frequency applications.
But wherever there's a chance of high transient signals occurring. So, for example, in your case, perhaps there's noise coming in from somewheres, or you have these 1, 2, 3, 4 large gain amplifiers here that may be trying to couple noise in it themselves, right? So you're going to try to prevent that from happening, right? And you got these electrodes here too that especially with these floating references may cause issues, right? So again, I don't know to what extent that might have caused here at this point, but definitely the whole floating references and that were going to be a concern by all means.
Yeah,
I think part of your PC board failure may have been also, this thing might be oscillating somewheres or something like that, right? Because of lack of a ground plane or things like that too, right?
Mm-hmm.
So,
yeah.
Anyways, it's something to investigate by all means.
Yeah, if I ever decide to properly finish the project, I'll definitely do a quick touch up on the PCB and add a ground plane, definitely.
Mm.
Okay, that's good for me.
Right.
Thank you.
Ron, any questions? We're kind of out of time, I think, anyways.
Yeah. I was just checking out the blog, the documents there, and for the block diagram at the output of the there's a VREF identified in the block diagram at a few points. Looking at the schematic, can you pinpoint where that is in the schematic? Just
yeah.
For my sake, I guess.
Yeah, absolutely. VREF is set. I can't point. If you look at U1C, the voltage divider at pin 10 sets the reference voltage. Okay. U1C, set as a voltage follower, outputs that reference voltage. So any connection that's connected to the output of U1C, I think it's pin 8, but I can't zoom in to see and confirm. But
yeah, I believe so, yeah.
Any connection that's tied to that is the reference voltage.
Okay.
And what's the purpose of that again?
To allow the transmittal of negative signals, because this is a single supply ground reference instrumentation amplifier. Because resting signals in the body are actually generally negative, it would be impossible to output those with just a positive supply and no offset. So it's important to give headroom for the signal to.
Okay. And I think you're being dependent on the input of whatever device you're feeding this into to have a decoupling cap to allow that to happen, right? You're actually transmitting all DC between 0 and whatever your VCC is, but you're making sure it centers on whatever mid-level reference value that is. Yeah. And again, that comes back to how that J2 should be wired, because at this point you would have two floating values, and I suspect a lot of hum and and things like that.
So, yeah, there'd just be two differential voltages with no reference.
Yeah. So that would definitely give you issues. Okay. All right. Thank you. Very good presentation.
Thank you.
It's unfortunate you can get it working, but that's all right. Yeah. That's part of the process and picking up from there. So we're going to break for lunch. And then we'll come back in the afternoon for there are two scheduled presentations. As far as I know at this moment, I think both are going to happen, but we'll find out in this afternoon as to what the situation is. But we will definitely have a presentation this afternoon, if not two. So please, if you have the opportunity, join us at 1:30, and we'll start our presentations at that point. So thank you very much, and we'll see you then. Have a good lunch. All right, so we're back from a quick lunch break, and we are going to have 2 presentations this afternoon, so that'll be exciting. We'll be able to listen to the 2 students show their wares and give us a quick report on their projects. I'd like before I start, just a quick reminder to the senior electronic and electrical students to remind them that although the SPL lab sessions are obviously terminated after this or as of last week, we still need to do work in the labs and that, so keep times blocked off for access next week and the week after, because you'll be expected to be present for those sessions. All right. Okay, so this afternoon, the first person on the list I have is Mrs. Afsana Bedza, and she will talk to us about her single-phase induction motor smooth start project. Afsana, are you there?
Yeah, I'm here.
Okay, so the floor is yours.
All right, so thank you everyone for participating from this presentation. My name is Afsana, as Mr. Metcalf said, it's Afsana Beja, and I'm a student in alternate energy. So today I'm going to present a project that says a smooth start for a single-phase induction motor. I'm gonna start by sharing my screen. Can you guys see my screen?
Yep, we see it.
All right. So as I've said, my project name is single phase induction motor smooth starter. So for the first time, for the overview. So we're going to see the definition of my project. What's my project about? We're going to see the applications where we can use a single phase induction motor. I'm going to be presenting the project and explain the project what do, and say how does this project function, give some output waveforms that I have done and in the lab, and then present the final design for my project, and then have a conclusion. For the first, I'm going to explain what is my project. So for starters, for induction motor, the induction motor is an electrical motor which produce current by using electromagnetic induction from magnetic fields of stator windings. And then a smooth starter, when I say a smooth starter, what I mean by that is like a device that protects those electrical currents from a high surge of electric current when the motor starts up. It's like when we try to plug in the motor at first, sometimes there is a high current that passes through it, and sometimes it damages the motor's winding. So my project here is going to explain how I can build a smooth start so that the motor can start with the low voltage at start, and then at the end it can go with the high voltage. So for the next slide, we have applications of single induction motor. I've explained what induction motor is, and I'm going to give examples, for example, where those induction motor can be used. We all have, like, most of us have refrigerators in our homes. So those induction motors can be used in our refrigerators. They can also be used in compressors. They can also be used in small fans. And mostly those induction motors, they're used in like small devices that has a small horsepower. For example, like 1 horsepower, that's where those induction motor can be used. So for next, I'm going to say what does this project do exactly. So I have a block diagram here. It's going to help me explain what does this project do. So I have here 120 volt VAC that goes into a switch. So 120 volt VAC is supplied from the wall. And then I have a switch that controls a light bulb, a comparator, and a transformer. So for this project, I haven't been able to use a motor from the lab. So I'm going to use a light bulb instead of the motor to display the outputs. So from the AC switch, I have 120 volt VAC, and then it goes to the transformer. I'm using a transformer of 24 volt. So the transformer is going to step down that 120 volt VAC to 24 volt VAC. And then I have signals from transformer goes to the full wave bridge rectifier. That rectifier is going to help me to convert the VAC voltage into DC voltage. So on the bridge rectifier, I'll be having 6 volt. And then from the bridge rectifier, it goes to the zero crossing detector. So a zero crossing detector, I'll be using a transistor to create a zero crossing detector. Then it will be able to give me like positive pulse voltages that is going to be directed to the integrator. And then the integrator will use those inputs to transfer the output to the comparator. So in the meantime, I have an RC delay where I'll be using like a resistor and a capacitor to determine like how long do I need my output to be displayed. So it's up to you to choose like how long do you want your output to be displayed. So for my project, I picked 2 seconds. And then the comparator goes back to the AC. So the AC, as I said, is controlling the light as my load, and then controlling the comparator and controlling the transformer. Next, I'm going to explain how does this project function exactly. So as I said, this is my transformer. So I have 120 volt VAC as a power supply, and then it goes to the bridge rectifier here at B1. And then from that bridge rectifier, as I mentioned, I have 6 volts from it. So I use the MC815 voltage regulator to regulate that voltage to give me a 15 volt. And then as my output here, it wasn't exactly, when I measured it with my voltmeter, it wasn't exactly 15 volts. It was around 14.78, 1480 something. So it wasn't exactly 15 volts. And then, so I have 2 capacitors here connected to the one on the input and the other one on the output. And I have here a diode. So what does this do? The capacitor 4 and capacitor 6, what this helped me in my voltage regulator is to help me to control the ripple voltage that passes through the voltage regulator. And then the diode, for my diode, I used 1N4007. So what did diode help me? It helped me to protect my regulator. Just in case there is an input short, maybe on the input, like where the C4 is on pin 1. If there is a short on that pin, the diode will help me to protect that short. And then, so from at the bottom, I have a transistor T1, and then there's 2 resistors, R1, R2, and R3. So what am I using with this transistor? This transistor, I'm going to use it to create what I called a zero crossing detector. So this zero crossing detector, as I said, I have a voltage that is going to come from B1 on this side. So the positive is going, the voltage is going to be is going to be applied through R1 and R2. So at the base, I have a voltage. So I need, in order to have the zero crossing detector, I need the base to be low And then, so I need the transistor to be off so that my output on the collector is high. So this transistor is switching from low to high. So as this voltage on the base goes low, the output of this transistor on the collector is high. So what this means is like, if the collector on my transistor is high, there will be like the output of the collector will be displayed on the base of T2. So it's switching from a low voltage to a high voltage. It's switching from a high voltage to a zero voltage. So that is what I call a zero crossing detector. And then from the T2 on the base, I have that voltage, what I call the pulsating DC voltage. So it's going to be applied through R4. So this L411N is my op-amp that I'm going to use. So on the inverting input, I have R4 and R5s. So the voltage from the collector of T2 is going to be applied on the R4, and then this rheostat that I'm gonna be used. So the voltages will be going through R4 and R5, and it will give me what I call a voltage ramp. So what is a voltage ramp? A voltage ramp is like a rise of a voltage. So when the voltage ramp on the inverting input is higher than the non-inverting input, so my output here is going to be high. Then this output from the L411 is what I call the voltage ramp. So that's the voltage rise from 0, and then it rises linearly. And then that voltage I'm going to be using it as my input on the LM311. LM311 is the voltage comparator that I'm using for my project. So the LM311 is a voltage comparator that compares two voltages to give out the difference, to give the output difference of it. So what I need from my project, I need this voltage comparator to compare the two voltages so that the output of it is low, so that I can have a current passing through the MOC 3010. So what does that mean? To have this MOC is an optocoupler. So to have the current pass through it, I need an output from the LM311 that is low. So how is that going to happen? That means LM311 has the voltage ramp on the inverting input, and then it has another voltage, 15 volt DC from here on the voltage regulator, and then I have a resistor R9, and then I have a capacitor here. So what this line here means, I created this line to create a time delay. So as I explained on my block diagram, I have an RC delay, so I need my output to be displayed in about 2 seconds. So the voltage here, the 15 volt is going to be applied through R9, and then this comparator is going to compare the voltage from the inverting input as my ramp and then non-inverting input on pin 2. So to have the comparator here on LM311 to be low so that they can have current passing through the optocoupler is that the voltage ramp here on the inverting input must be higher than the voltage of the non-inverting input. Then if for example, if the non-inverting input is greater than the voltage at inverting input, the output of the LM311 is going to be high. At that time, if the output is high, there will be no current flow to the MOC11, and I need a current to flow this to flow on my optocoupler so that it can trigger my triac, the Q1 here. So the voltage ramp here from the L411 will need to be higher than the voltage on the non-inverting so that I can have a current passing through this. So when current passes through the optocoupler. This optocoupler, we have to trigger the triac here. And then this triac will trigger it so that the lamp, as my load, instead of the motor that I'm using, will start from a low voltage and then increase linearly to a high voltage. So that's how exactly my project works. So I used here a switch 1 here. So I wanted to control like the voltage on the RC delay and then the voltage at the lamp. So I used this, and I used the double pole double throw switch so that I can control this signal from the RC delay from R9 and C5, and then control also the voltage here on the load. So my next slide is the output waveforms. These output waveforms, I obtained them when I was doing my breadboard. So this channel 1, the yellow waveform you guys are seeing here, is the yellow, sorry about that. The yellow waveform here is the waveform at the base of T1. So when we go back to this this schematic, so the base here, the voltage, the fully waveform from this base here is the one that is here. So whenever, and this, the next waveform, the blue one, is the waveform of this collector here. So the output from this collector. So as I was saying, from the zero crossing detector, whenever the base voltage goes low, the collector side will go high. So as these ones, so the transistor will keep switching from high to low, and then it will depend if it's high, like here, the voltage was high, and then my output was high. Sorry, the voltage on the T1 here on the yellow was low, so my output on the transistor collector here was high. So these pulsating voltages is what helped me to charge this. When I go back to my schematic, it's what helped me to charge this C1. So whenever this C1 starts charging, it provides a linear voltage that will help me to, so that's what I wanted, to provide like a linear voltage that increases from a low voltage then to a high voltage. So whenever this C1 here, the C1 on T2 starts charging, it will provide a linear voltage so that whenever this T2 is off, this one will start charging. And then that's what I will find my voltage ramp here. So on this waveform, the voltage ramp is the third waveform here. So my voltage increases and then go back to 0 and then increases and then go back to 0. So this is what I call a voltage ramp. So my voltage needs to be from a low voltage, then start from a low voltage and then go to a high voltage. So the next slide here is my final design for my project. So this is a concept drawing that I had to redo. And then this is my PCB layout for my project. As shown here, so on top I have a lamp to display my output. And then this is my PCB. And I used 2 transformers. So one was giving me a plus 15 volt, and I used the other transformer to give me a minus 15 volt. So as a conclusion for my project, I think this is a really interesting project to use like in our daily life, where we are kind of using the motors in everything we do. So if we have like every motor, like you have maybe a fan at your home, and then it's in the summer you want to have a fan in your home, and then whenever you plug it in, it starts with the high voltage, and then the fan breaks. You go to buy another one, and maybe that the second time the fan as well breaks, that'll be a waste of money. So I created this project so that for small devices that uses small power, this smooth starter will help them so that it can start with the low voltage so that it can prevent the large inrush current that come at the start when the voltage is when the motor is starting. So for my conclusion on my PCB, on my project was working on my breadboard, but when I tried to do it on my PCB, it wasn't working. So what happened is I connected it as I showed it here, and then whenever I tried to switch, like maybe put this switch here, the light come for 2 seconds and then it goes off. So it does the inverse. So I want my light to take 2 seconds for interval and then come slowly. But instead, when I tried to do it on my PCB, the result was the light come for 2 seconds and then it goes off directly. So that means my output here, the output from the voltage comparator, it's still high. It doesn't go low. So I haven't been able really to figure out why is it happening. Some ideas that I had was maybe like the voltage here at the output of the comparator was still high, and it needs to be low to allow the current to pass through the optocoupler so that it can trigger the triac. So that's one of the problems. I thought maybe it was causing the PCB not to work. So for the next, I'm going to demonstrate what's happening exactly at the moment. So can you guys see my lamp?
Yes, we can.
All right. So I have my switch on off, and then when I try to plug in the 120 VAC, so what happened is the light goes on for 2 seconds. It's not roughly like 2 seconds, like 1.7 seconds, and then it goes off. And then when I try the other position, so it does exactly the same thing. So the light flashes and then go back. It's like the output is high and then go back. So the output doesn't go low. So it doesn't allow the current to pass through the optocoupler. So that's what's happening now. So I'm trying to I didn't figure out at the moment why this is happening. So thank you. That was my presentation. And if you guys have any questions, I can try to answer them.
All right, thank you, Afsana. Very good presentation. It's unfortunate your project didn't work at the end, but you still were able to tell us obviously why, and and that's part of project development too. Is sometimes the projects don't work. So, can you bring up your schematic for me? I have one question, and I'll pass it off to the other advisors. To that point, There you go. All right. So I was looking at your schematic when you were presenting there, and I just happened to glance at the one that you submitted to me, and I noticed that we were 2 versions behind, which I was like, wow, that's a big difference. And you know, and that's whatever. It is whatever. At least your versions, indicate that. So I was able to determine that. The one thing, though, there was one thing that struck me as a critical, as a difference, that one of the ones that stood out for me as a difference was I noticed in version 3.1 that I have in front of me on the TB4, the lead that's going upwards to the switch 1 there, to pin 2 of switch 1. You know which lead I mean? On my version, there's a fuse, a 3-amp fuse, and on your version, the 3-amp fuse is omitted. So I was wondering what was the decision to do that.
Yeah, it's because at the final project, I was planning to use a fuse, but for my PCB, I ran out of time, so I wasn't able to print another PCB. So this is the circuit that I used to print the PCB. That's why.
So what dangers, does it entail any dangers? Or, I mean, a fuse is, it's usually not something that we omit due to, it costs 10 cents, or we want to cut the budget, or in your case, whatever decision you made. So what consequences does it have that the fuse is not in your final product versus on the schematic? Obviously, you thought it was required there at one point, right?
So I thought the fuse could help me to prevent, like, if there is a high current in my circuit, so the fuse will help me to prevent that current in my circuit.
So what do you mean by will help you prevent the current? What is the fuse there for? What is any fuse there for?
So the fuse will help me because that pin is connected to the neutral, to the 120 neutral. So I wanted to use that fuse so that it can break the circuit whenever the current is high, more than my load. Because for my load, I'm using 1 amp. So if I have more than 1 amp, the fuse will help me to break the circuit.
Okay, but this is okay, that's fine. So, but again, what is the fuse trying to protect? It's true that you're saying, okay, I don't want to load more than 1 amp, but yet you have a fuse there that is, in my schematic, it's 3 amps. So obviously you're allowing an overcurrent based on the 1 amp. But in your courses, and especially in your courses with me in PV, we talked about what a fuse is for. So what am I trying to protect when I put a fuse in anything?
You're trying to prevent a fault in your circuit.
No, not at all. The fuse will trigger on a fault.
Yeah.
The fuse will not stop a fault. In fact, it's the other way around. The fuse will open when a fault occurs. So, but we don't want the fault to cause what? What are we protecting? Whenever we have a fuse in the circuit, what are we trying to protect? Which component are we trying to protect? In all those PV circuits that we had there in my PV class there, we talked about fusing and putting fusing in, right? And what happens to the temperature of the wire?
It increases?
Yeah, it increases until what happens physically?
Until
if there's insulation or any kind of material around it, what happens as the temperature increases?
So
if you have a wire in the wall and you've got wood structure, you've got insulation.
The wire could overheat.
There you go. It could catch on fire, right? It will overheat and catch on fire. So fuses are there to protect a wiring only. Okay, when we have fuses, it's a big misconception that fuses are there to protect the electronics and whatever. Fuses are there to protect the wiring so that the wiring does not exceed its rated capacity, ampacity. Okay, so in your case, you chose a maximum capacity of 3 amps.
Yeah.
And then by removing the fuse, now you're dependent on whatever wiring is going to be at the output and whatever protection it may have. Hopefully, it has fusing limitations, right?
Mm-hmm.
Okay, so that's a pretty critical device to have omitted on your PCB board, in my opinion. Okay.
Okay. Yeah.
All right. I'll. If anybody else has questions there, that was my.
I'm going to offer a theory as to what went wrong with the between the prototype and the finished product, but I'm going to maybe take the last 2 or 3 minutes to do that. Anybody else has any other questions? Please bring them forward.
I don't necessarily have a question, but maybe an observation. Afsana, can you bring up your PowerPoint slide?
Yeah.
Particular you had a picture of the oscilloscope in the lab.
This one?
Yeah.
Yep.
The oscilloscopes that we have in the lab have a feature where you can save a screen capture on a USB thumb drive, which actually the USB port is shown in this picture. And that would have been a better visual representation of this graph if you would have taken a screen capture from the oscilloscope itself. Just note for future reference.
Okay. Yeah, because I took this picture when I was trying at first when I was doing my test on the breadboard, and I didn't take any, so I didn't get the chance to get in the lab again and do the test on the PCB, so that's why I used this ones.
Right. I mean, it is a valuable picture for your presentation and all. It's
yeah,
just,
exactly.
You can get a good screen capture from that, and just would have came out a little more professional, but that's a learning thing, of course. Sure. I don't know if anybody else had anything to add or a question there.
Yeah, okay, Afsana, why do we care about zero crossing detection? What is the purpose of you have zero crossing detection, which is controlling your indicator and producing a ramp. Why do we care about zero crossing detection in this application?
So we care about it because we need the transistor to saturate. So it means if the voltage at the base is high, and then the output on the collector will be low. So the zero cross, it helps like between the switching of the two signals. So it helps for the switching between the switching of those signals. It helps to detect the 0 point of the voltage.
Yeah, but why do we need to know? Why do we need to keep track of? Why do we base our control on the timing of the input power waveform? Why do we care about zero crossing detection? What purpose does that serve? Yet you explained how it works, and you're right.
Yeah.
At zero crossing, T1 turns off, which in effect turns on T2, and that resets the ramp out of the integrator. But why do we care?
Because it happens in different angles. So it can happen from like 0 degrees and then go up to 180 degree. So we need the, how do I say this? We needed to detect like the voltage between those change in the triggering angle.
Yeah, I think you're pretty much onto it. Could you maybe clarify a little bit and talk about the how did you intend to control the voltage delivered during startup? You wanted to turn on the triac at a specific time.
Yeah.
But relative to what?
Using a low current through it. So I was based with the voltage comparator. So if the output of the voltage comparator is high, that means the output from it is going to be low. But if the output of the voltage comparator is low, no, if the voltage comparator is high, that means there will be no power at the load.
Yes, that's correct. But how do we measure, if we want to control the voltage delivered to the load, and we want to do that by varying the delay angle upon which we trigger our semiconductor switch, our triac, what do we measure the delay angle relative to?
Oh, through the signals from the collector of T1.
Well, actually, what we want to do is we want to measure it relative. Our output is actually going to be, a triac is a bidirectional switch, so we have to control our triac relative to the zero crossings in the input AC waveform.
Yeah.
That's what the zero crossing detect does. Okay, does anybody else have any questions?
I would maybe have one. Could you bring up your schematic, I guess? Just again, it's maybe more of a design question, and I just want to know your thoughts on this, Afsana, more than anything else here. If I was looking at this, I noticed you have the two transformers there. You have B1 and B2, and B1, amongst other things, is providing you with your 15 volts DC, and B2 is providing you with a minus 15 volts DC, and that's fine. I was just kind of curious as to why not have a circuit that actually combines those two to be able to get your plus minus 15 volts off of one transformer, as opposed to having the two separate like that. I'm just, did you consider that, or
like trying to use like one circuit instead of the other circuit?
Yeah, it's very common. It's very common when needing plus and minus voltage supplies to center tap a transformer and then obtain the positive on one side, the negative on the other side with reference to ground. Okay. But in your case, you're showing me that there is actually two transformers and two diode bridges there to do the same job. So, I mean, my question here comes into a product manufacturer where the cost of one transformer is half price of a cost of two transformers, and transformers are relatively speaking very expensive pieces of equipment, right? So I don't know how much you paid for yours, but I'm sure they were probably some of the major costs in your project. So one of the ways to try to alleviate that cost is to say, can I do it with one transformer? And I'm legitimately asking the question because I'm curious as to if you could have done that, you would have saved yourself money. But is there a purpose where you couldn't, or a reason why you couldn't do it? I noticed on the first transformer there, the output on that 7815, you got that little transistor and all that. But could we have done the same thing by combining those two circuits together? Is that still possible, or is there a grounding reference issue or anything like that? To the best of your knowledge, I'm not, Do you think that would have been possible, or?
Yeah, it's actually possible.
Yeah.
Yeah, it's possible to combine like using one transformer to set like, but the issue I had, it was like to do that, I need like from the input, I need like a positive 20 volt and a negative 20 volt so that I can use the voltage regulator to step it down to 15 or minus 15.
Yeah.
And I didn't have the negative and 20 volt and the plus 20 volt. So I thought maybe this will be the way I can do it.
Okay, well, it definitely is one way of doing it.
Yeah.
I just think that you could have, and again, hindsight is always 20/20. I think there was probably a way of being able to do it with just one transformer and diode bridge, having not necessarily the this type of diode bridge with the same outcome, and then again using the 7815 and the 7915 to get your plus and 15 volts and do the rest. You just would have, again, I'm pretty sure if you looked at your parts, your bill of materials, and you took off one of the transformers, you probably are cutting down the cost of your product by a lot just by doing that, right?
Yeah, exactly.
All right. We tend to go to this type of configuration there, the rectifier bridge. The Wheatstone bridge. We really like these configurations because we see them all the time. But there are other configurations that allow us to do what I'm talking about, right?
You have to combine them to have one.
That's right.
One circuit, yeah.
Exactly. All right. So again, I was just wondering if there was a reason that you knew why you didn't do that. But again,
I'll focus on it actually after this.
Thank you.
Yeah.
So just real quickly, in Afsana's defense, the addition of the fuse, she originally purchased a single pole, single throw switch to control the AC, which had an integrated fuse in it.
Oh.
And it wasn't until later iteration, matter of fact, an iteration that was so late that we got jammed for time. She was unable to produce her final board. We had to go to a double pole, double throw switch. The reason being that if you look at the comparator, we've got the ramp coming out of the integrator, right? On the inverting input, but on the non-inverting input, we initially had a building ramp to give us the RC time constant.
Yeah.
Control the delay angle, but we finally discovered, I say we because we were working on it, that we had to have a decaying ramp. So we had to start with a charged capacitor. And then short it to ground so it would decay, so that instead of increasing from 0 to 180, from 180 to 0, as we saw with the initial brightness disappearing, we had to invert that control function so that it would build from a delayed angle to a very small angle of 0 degrees.
0 degrees.
So that's Afsana has been doggedly determined to get me to run her another board so she could finish this in time, and I feel I let her down, mostly because of now it's presentation week, and I do. If you're going to come into school today, you can try that.
With what I had.
Yes.
Well, that's exactly like I mentioned at the start. There are projects, that's the risk of doing any project is not being able to come to a fruitful conclusion at the end as far as completion is concerned. But nonetheless, you can also do like you have done, which is basically, be able to tell us why the failures occurred and what you would do in the future so that if you ran this project again or a similar project, you'll obviously be successful at that point, right? So there's tons of people at university that make their thesis on why things didn't work as opposed to work. And they don't start their thesis by doing that. They start them by trying to prove something and then discover they're actually proving it doesn't work, right? So there's nothing wrong with that. All right. I think that's it. We're out of time for the question period, Afsana. Very good. Thank you. You answered well. And we'll take our break and come back at 2:30 to have Mr. Din Aminu talk to us about his sump pump level indicator project. And that'll be the last presentation for today. So please come back and see what Mr. Aminu has to say about his this project. Thank you.
All right, thank you.
Thank you, Afsana.
Yes, thank you, Afsana. All right. We're back for the last presentation here. We seem to be Afsana still got her presentation online there. Afsana, if you can hear me there, could you release the screen, please?
Oh, sorry, my bad.
No, that's fine. There you go. Thank you. Okay. So at this point, we're going to listen to Mr. Din Aminu present on his sump pump level indicator project. So, Mr. Aminu, are you ready to present?
Yes, I am. Can you hear me?
Yes, I can. So, and we can see your presentation on the screen. So you can go ahead and have the stage.
Okay, thank you. So, good afternoon, everyone. My name is Din Aminu, and I'm going to present my project called the Sump Water Level Indicator. So, can you see the big screen? Can you see my slide?
Yes, yeah.
Yes, we can.
Okay, perfect. Okay. So, on this slide, we can see that there's a flooded basement. So what can we do to avoid that from happening is to install a sump water level indicator. So basically what sump does is to drain and collect the water that usually accumulate in the basement of houses. It drains that water out of the house. So as long as the sump works, the homeowner is fine. But it becomes a problem when for some reason the sump does not work. So to notify the homeowner of that problem, an electronic system called sump water level indicator can be installed in the house to constantly monitor the water level in the sump. So during my presentation, I'm going to try to describe how the circuit works, how the different components interact with each other. So here we have I have the preview of what I'm going to talk about, and okay. So here I will start by explaining my block diagram. I hope you guys can see.
Yes.
Okay, perfect. Okay, so on the block diagram, we have on this side, we have the water, and in the water, we have the sump, and we have we have a sensor array, and so basically the sensor array is just a 2 feet non-conductive pipe, and we are going to drill 10 holes around the pipe to put bare copper ring in on the PVC. So when the water and that 2 feet non-conductive pipe, you are going to put that in the sump. So when the water level rise, so there's conductivity between the copper rings. So due to the conductivity, the water level is sent as an electronic signal to the dot bar LED driver. So the dot bar LED driver is LM3914. So that LM3914 will interact with the dot bar display driver. And the dot bar display is 10 10 LED bar graph display that will indicate the water level in 10 increment. So when the water level is low in the sump, we have just one LED on. So as the water level rise, more LED are on till we have all the 10 LED of the bar graph display on. So when the 10 LED of the bar graph display is on, that means the sump is full of water. So we are going to have warning signs. And here the warning signs are the flashing LED or a buzzer, a flashing LED that will flash to indicate that the level of the water in the sump is critical. And at the same time, a warning sound from the buzzer will sound to alert the homeowner to let them know that the sump is full. They need to go and check the sump and they have to take action, otherwise the basement will be flooded. And also beside the buzzer, we can see a silence push button. So basically that button is just to silence the noise made by the buzzer. So and the wall electronic circuit of the sump water level indicator is powered by the 12 volt. So 120 to 12 volt DC, 120 AC to 12 volt DC power supply. Okay, so now I'm going to talk about my schematic. So on the schematic, we can see we have 10 terminal block. So before I will talk about the terminal block, I would like to talk about again the sensor array. In fact, the copper ring we put on the length of the sensor array, we are going to put we are going to add individual wires on each copper ring that will connect to terminal block on the PCB. And each copper ring, there is resistors, as you can see here. There is resistors in series with each copper ring. So basically, those resistors, they will cause variable biasing. They will cause variable biasing of the transistor Q1 we have here. And basically, the transistor will get more and more bias, and it will send the water level, the level of water. It will send that as an electric signal to the LM3914. So basically, at this point, the LM3914 receives the signal from the sensor array through the transistors, and then the LM3914 will interact with the bar graph display. So as I said earlier, the bar graph display is a 10 LED. So the more and more water fill the sump, more LED will be on. So at the 10th LED, we are going to have so before that we have here a transistor. So that transistor will first of all, I will say, sync the current received from this part of the circuit, and based on the amount of I'm sorry. So this part of the circuit will send this a signal to the flashing LED that we have here, and it will indicate that the sump is at his highest level, and then this LED will be flashing to let the homeowner that the sump is full, and at the same time there is a buzzer connector with the flashing LED, and the buzzer will sound also to let the homeowner that his sump is full. And we have a transistor in line with that buzzer. That transistor combined with a resistor, they both will be used to I will say sync the amount of current they receive from the power supply. So I will basically say this is what I have to say regarding my project, and here is the part. Sorry. So here is the before that. So I wanted to show the part list, but I think it's not on that part. But basically, this is what the project might look like if I was able to finish, because due to some technical issue, I was not able to go further in more in details with the project. But as you can see on this picture, you can see a bar graph display with all the 10 LED are on. So in that case, that means the sump will be full, all the 10 LED will be on, and at the same time we'll have the buzzer and the external flashing LED that will make the buzzer will make sound, and the flashing LED will flash to let the homeowner know that the sump is full. So in conclusion, what I can say is basically the best way to avoid a flooded basement is to install a sump water level indicator, and that is constantly monitored by sump water. So I'm sorry. So to sum up, the best way to avoid flooded basement is to install a sump that is constantly monitored by a sump water level indicator. So I won't be able to do any this demonstration because, like I said, I run to some technical issues. So here is the end of my presentation. Any question? And I have reference and bibliography.
Okay, thank you, Din. Nice presentation. I think just give me a second here. I gotta just record something. There you go. Perhaps we could look at your schematic briefly.
Yes, sure.
All right. I was a little intrigued because I can't really tell which version your version is on the schematic. Do you know what version your schematic is?
1.6.
Okay, it's 1.6 really, because you submitted version 1.6, and I definitely have some different. There's differences between my schematic and yours.
Of my mistake. Yes, I think I have an older version of my schematic.
You have an older version?
Yes. I'm sorry for that. Sorry for that.
Okay, well then that makes me a little even more misunderstanding. So first of all, you shouldn't have different versions with the same version number. Okay, that's important, right? Okay,
yep.
But second of all, let's talk then about your switch for your silent switch. Okay,
yes.
On your older version, according to you, this is the older version. You have a toggle-like switch, right? A single pole, single throw switch, right?
Yes.
Okay.
Yes.
On my version, it is a push button switch. All right. In the open, normally open state. Okay. So my question to you is, what's the purpose of that switch if it's push button? And and how does it work to silence the? And again, on mine it's a buzzer. On yours it's an LED. So I don't know what the,
Yes, there's a miss. Like I said, I'm very sorry for that. On my presentation, I think I don't have the correct version because actually it was updated to have a toggle switch.
A toggle switch? Okay.
Yes, actually the idea is just to switch off the wall, the buzzer.
Okay, so that's what you have is there, but you don't have a buzzer. You have an LED instead. Whereas I have a push button switch with a buzzer. Okay, so yeah, it makes more sense to have a toggle switch than it would to have a push button switch, right?
Yes.
All right. There was that.
It makes more sense to have a buzzer than an LED.
Yes, it does. Yes. Yeah, it does. The other question I had, I guess, well, there's two more questions. So you said that the buzzer sounds and the LED, I think it's D1, blinks.
Yes.
So how does it blink? What causes it to blink?
Okay, so like as I said, when the sump is when all the LED of the backgraph display are on, that means it's critical. So at the same time, it will send a signal to that flashing LED. It will flash yes, it will flash basically, yeah.
So is that LED a special LED that it flashes, or?
Yes, it has a flashing a built-in system that flash right away.
Oh, okay. Because I don't see that in your parts list that you supplied either.
It's supposed to be there.
All I see is an LED called D, and it says LED red diffused LED, and then it has its size and its package, and that's it. All right, and then it gives you a part number and so on. So it's not indicated there. So it's important that you your obviously your parts list has to reflect that. Yep. And even I would even put a note in your schematic here indicating that, because if I was repairing your device here and D1 is bad, I'll just replace it with another LED. It's a red LED, I'll replace, and then all of a sudden the LED doesn't blink anymore, right? Because it's not the same LED. So you have to be careful. And the other thing is it's listed as D1 in your schematic, but in your parts list it's just listed as D. So that leads to confusion too. All right.
Yeah, I'm sorry about that.
No, all right. And my last question here for now is you have 12 volts, all your source feeds there on top, 12 volts, 12 volts, 12 volts. Where do those 12 volts come from?
So they come from the 120 volt to 12 volt wall mounted adapter.
Okay, so how would I know that looking at your schematic?
That's why I put the wall mounted adapter on the top right left corner.
No, but how would I know that though? That there's a connection between you have that barrel connector symbol there. How would I know that the center pin of the barrel connector feeds all of that? You understand what I mean there?
Yes, I get you, Mr. Metcalf.
Like you've got it all labeled as 12 volts all over the place, plus 12 volts.
Yes.
But then at the power jack connector, you don't have it labeled as such. So there's no way of me knowing in an electrical sense that there's connectivity between that. To be honest, what you're showing me there is just really there's a barrel connector that connects to ground and is just kind of open there and not connecting to anything, right? You have to label that connector on the top left. You have to label that one plus 12 volts also.
Okay, yeah.
I also want to point out your schematic is on screen is very difficult to read. I'm assuming it's a bit capture, a screen capture, and it's very, very difficult to read. And even the one you submitted to us is very difficult in the fact that it's not black and white; it's grayscaled, and it is also very fuzzy. So it makes looking at and analyzing your circuit very difficult. The one on the screen, to be honest, is almost illegible there. I have to refer to the one you submitted to understand what the part descriptors are because I can't read them off screen.
I'm sorry about that. Yeah.
All right. Anyone else?
Yeah, I'll add to what Mr. Metcalf was saying there. I think Din. Well, first of all, I'd just like to say, Din, you came up against a few problems, and you had a hard time, but you still came and presented. So I think that we all owe you applause for that. You know, you're being a man and stepping up to the plate here, and that's great. So thank you for that. And I did want to just mention in your defense, Din, and in following up with Mr. Metcalf said, is Din actually took the description of that part directly from DigiKey. So we should call up DigiKey and tell them about their sucky description. Anyway, still, I guess we could probably make that addition there. So I do agree with Mr. Metcalf. It would be nice to see somewhere that it is a flashing LED so that we don't, when we do go to replace it, yeah, that's true. I mean, if we follow your parts list, we would actually replace it with exactly the same flashing LED.
True that. Yeah. I wouldn't want to be the one that orders 50 of them because I need an LED order at the same time and discover there's one that's going to work in his circuit and 49 that are going to be blinking all over the place afterwards. Though.
Yeah, that's right. Yeah.
I think a note on the schematic, just because it's such a particular part anyways, even if it said blinking LED in the parts list, I think a note on the schematic saying, D1 is has a built-in blinking feature or whatever would definitely be in order. That's what notes are for, right? To point out the really weird stuff and not apparent stuff. Okay, so yeah, well that's good for Mr. Broad to have pointed out the fact that that is a DigiKey description and number. DigiKey again is not always the best at naming things either. They do things in bulk too, right? So.
That's right, and I think what I would prefer there, I guess if we went to version 1.7 of the schematic, that the D or D1, of course you're going to make that consistent, but that on your schematic there it says D1, so that D1 would actually have some text next to it, and usually we'd include the color there, and in this case maybe we just say flashing red right next to the diode symbol, which would really help, and then we wouldn't need a separate note. But definitely the function of that LED should be shown there, right? So it should be written there also critically high level or something like that, right?
Okay.
Again, I'm following like Mr. Metcalf said. I can't actually read the text on your diagram on that you have displayed on screen, so I'm following the one you submitted, which has the buzzer in it. Maybe you could talk a little bit about that buzzer, is that buzzer when it is on, and we notice that there is a toggle switch that controls the kind of the silence function there. When it is on, so the toggle switch is closed and the level has reached that critically high level, and therefore, like you said, all 10 LEDs, including the upper LED where the base of the two transistors will be tied to, then when that state is met, or that condition is met, and your Q3 then is conducting, what happens with that buzzer? Can you talk about that buzzer a little bit? Because I know we did have kind of an issue with that buzzer, didn't we?
Yes, yes.
Maybe talk to people about the issue you had with because you had ordered a particular buzzer, and I think you didn't notice what type it was, and you had some issues. Can you talk about that and kind of explain that a little bit?
Yeah, sure. So the first one we've ordered was an externally driven one. So we have to use we have built in a circuitry to make it sound. So later on, we decided to order a new one that will be internally driven, that we don't need to create a new circuit to make it sound. So we can just put it in our some level indicator.
Your mic is chopping up a little bit there. Maybe just adjust your mic there.
I'm sorry. Can you hear me?
I think so.
Can you hear me now?
I seem to be able to. I can hear you. If you talk a little bit more, I'll be able to tell for sure.
Okay,
it was just chopping in and out.
Okay, I'm sorry. Can you hear me now?
Yes.
Okay, I'm very sorry for that. So I was saying that first of all, we order a buzzer that was externally driven. So we have to build a circuitry to make that sound. So later on, we decided we are going to order a new one that will be internally driven. So we can just put that in our sump water level indicator, so that will make it easier for us.
Okay. I thought that was good that you explained that. And so that was to kind of save on circuitry and not have to go build a separate oscillator circuit then.
Exactly.
So what happened when you connected your what we call an externally driven buzzer? Okay. What happened when you tried to hook it up?
There's no sound. No
sound at all. I appreciate you using the word sound there. I think that's the correct term. Maybe you picked that up from earlier presentations. Yeah. Did you talk about the sensor array? And what is happening there with that sensor array? I don't recall what you said about it, but
sure.
So yeah, maybe elaborate a bit on that.
Yeah, so like I said, basically the sensor array is a 2-feet non-conductive PVC pipe. So we drill holes around the pipe, and in order to put copper rings. So basically, those copper rings we allow the conductivity of the water, and from then the water will be sent as an electric signal to the rest of the circuit. Okay. So basically the copper ring, they short together to get electric signal from the water.
Okay, so let's say that the water level is, I'm trying to just read, I think it's 0 through 10. Yes. So let's say that the water level is just above the 1. So probe number 1 there, electrode number 1. What is the difference between having the water level at electrode number 1 and then at above electrode number 2? What changes in the circuit?
It won't change that much because we are still at the low level. low level, that means we might have on the bar graph display 1 or 2 LED on.
So let me rephrase the question. So let's say that you're like I can't control your pointer, I guess, and you wouldn't see mine, but let's say, can you just put your mouse pointer right at electrode number 1?
Yeah.
I don't know if you can do that for me.
Yes. This one? Can you see?
I don't know. Am I seeing a mouse pointer? Anybody else seeing a mouse pointer? Maybe I can't see your mouse pointer.
No, I can't see it either.
Okay. I was hoping we could do that, but so if the water level is the water level's all the way at the bottom of the sump. It's like at 0, right? Yes. How many LEDs are on?
Just one.
If it's at 0 and it hasn't reached 1. Like
okay, no, there's none LED on.
None are on. Okay, perfect. So the water level rises. So we get a little bit of rain. Some water goes around the house and then goes into the sump like it's supposed to. And the level rises to electrode number 1. What has just happened as soon as that happens?
There's a conductivity between the copper ring of the sensor array.
Between which copper rings?
0 and 1.
Between 0 and 1. And what does that do? What effect does that have? Let's talk about the direct effect. I don't want you to go all the way to the output of the device here and just tell me that an LED comes on. But what I want you to do is tell me what's the direct effect of that happening. So you understand what I'm saying?
Yeah.
Okay.
Yeah. The water will become an electric signal.
Yes. And then what happens as a result?
As a result, one LED will be on.
Okay, so what I want you to do is explain not the LED itself, but what happens directly. Like you're skipping from the input all the way to the output. What I'd like you to do is maybe I can what I'd like you to say. I'll make it even clearer here. What happens to Q1? Transistor Q1.
It become more and more biased.
Aha. All right. So as the water level rises, what is happening to the base current?
The base current, we say increase?
Increasing. Why is that happening? What about the topology of the individual probes or electrodes, I guess, in your sensor array, and how they're connected with the resistors there? How are they connected?
They're connected in series.
Are you sure about that?
No, in parallel, because
I guess that was the only other one, right?
Yeah.
Yeah. So they are right. They are only connected in parallel when what is true though?
When there's conductivity.
Aha. So when the water level has surpassed the level in question, right?
Yes.
Yes, exactly. So that's how this is working, isn't it? And so your array of your sensor array is actually causing an increasing base current with increasing water level, is what you would say then, wouldn't you?
Yes.
Yeah, very good. And then what is that doing? What's the result of that? At the collector of Q1 then. Or the collector emitter junction.
Reduce the current?
Does it reduce? If you have an increasing base current, so let's say the water level's rising and you have an increasing base current, what are you going to have on the collector emitter circuit?
No change.
As the base current increases, you'll have no change on the collector emitter in the collector emitter circuit.
Oh, the current will increase too.
Yeah, right. You're going to get an increase in the current on the collector emitter circuit, and therefore an increase where?
At the base?
If you go all the way down to pin 5 of the LM3914.
Okay, the input of the LM3914.
Yes, exactly. And then what happens as a result?
Then we have an output on the other side.
Then the LEDs change proportionate to the current. Exactly, right? Yeah. So that's an interesting it's an interesting little circuit. You know, it's a very simple way to control some LEDs based on, well, actually based on any it's just an electrical input signal, right? And so we could modify this to do anything that we want. It just happens to be monitoring water level. But, anybody else have any questions? I can think of another one maybe if you want.
I had something to add actually to the previous conversation in regards to the formatting and differences of the schematic document. But Din, could you specify to me what the date stamp is on the schematic that you have here?
Okay, so based on what I have here, it's supposed to be May the 5th.
Is it May? It seems like March to me.
Okay, I have May. The last version was May the 20th.
The one that you're showing though right now, what's the date on that one?
The date, okay, might be March, yeah.
Right. I'm seeing the same revision number. This one's dated March 18th, but the schematic we're looking at is May 20th, but the same revision number.
Yes,
and it's
Mr.
completely
Metcalf's,
different.
2 months.
Yes, Mr. Metcalf's comment definitely rings true here, is that you can't have two different versions of your schematic with the same number. You got to change that number every time, right? Every time you make a change. If it's a major change versus a minor change, then maybe it's, you know, you're going to adjust the number differently, but okay, it still needs to be adjusted in some way.
Yes.
Did you keep previous versions, or did you save over and over on top?
I keep previous version.
Okay, because I just noticed that, for example, your file name doesn't have the version number inside the file name either, which is always a good thing to do.
Yeah, sure.
That's that way you don't run into these problems, right?
Yeah. Thank you.
I guess I have another question if nobody else does.
Well, I have a question, but Ron, if you're going to ask the question I think you're going to, I'm going to save mine for after. Does it involve the LEDs at the output?
Yeah. Actually, it's kind of two questions.
Okay, you ask your questions, and I'll wait, and I'll ask mine after. How's that?
Well, maybe I'm going to ask your question, though.
Well, that doesn't matter. Then it'll get asked. It's just as long as the question gets asked.
All right. Okay. This could be a two-part question depending on how you answer it. But anyway, let's start with this. In most LED applications, there is a dropping resistor or a limiting resistor in series with the LED. You chose not to put one in here, and I know we did have a discussion about this at one time, so you probably know the answer to this. Why in this circuit is there not a dropping resistor in series with each LED? The ones I'm referring to, by the way, are the actually we can refer to both. Actually, the 10 LEDs on the output of the LM3914. We can start with those, but I'm also going to ask you about D1 as well. So let's start with the LEDs that are on the output of the LM3914 first. Can you answer that question as to why that they do not have limiting resistors in series with them?
Okay, I will say because we use the LM3914, there's no need to use any more those resistors.
And why though? You're right. Okay, you're right that since you're using the LM3914, that eliminates the need for the dropping or the limiting resistor. But why? That's really what we want to know.
Okay, because the LM3914 provide analog display.
Is it? Do you really want to call this an analog display? Do you want to revise that? An analog display is infinitely variable, and this is only variable in 10 steps. So I don't know if you want to call it analog.
Or digital display, because we have
it's
one.
A digital display, okay. But let's talk about the individual. Just look at one of them, like pin 10.
Yes.
Why does that LED not need a dropping resistor? And you're right to say that the LM3914 doesn't require it, but why doesn't it require
it? Okay, so basically because of the fact that the IC or the IC there, the LM39 already provide that
what does it provide? That's what we want to know.
Provide, we say, is regulation. A kind of.
Okay, I guess it is a form of regulation. What kind of regulation?
A regulation of the current in one way.
Yeah, it does regulate the current, so it sets a constant current, doesn't it? How is that current set? How do you set it? Can you set it yourself, or is it fixed from the manufacturer?
We say it's fixed from the manufacturer.
Nope. Try again.
Okay, I recall yes, we can vary the current.
Yes, you can vary it.
Can vary the current, yes.
And how would you do that? Let's say that I wanted to make these LEDs brighter. I mean, obviously you're going to respect the limits of the LEDs according to the data sheet. But let's say that the current through the LEDs is currently 10 milliamps. No, yeah. What would I do to increase that current to 20 milliamps, say, for example? I don't need you to get specific into numbers, but I mean, just explain very basic sense. How would I do that?
Okay, maybe connector pin 5 of the LM39 to a voltage supply.
Well, pin 5 is telling. What does pin 5 do? Let's ask that question. Does pin 5 set the brightness, or does it do something else? You know what pin 5 does because you told me a few minutes ago.
Yes, it's more like, yes. More like input.
Yeah, pin 5 is running right off the collector of Q1. So you explained to me already what that does.
Yes.
Right. That dictates the number of LEDs that are on. We already know that.
Yeah.
You said that
Yes.
already. But what if I want to adjust the brightness of all of the LEDs? You don't remember? It's okay if you don't know, you can say. I mean,
I'm just trying to remember. I know we talk about it, but
yeah.
I don't have it.
So you can actually set the LED current by setting the current into a specific pin. I'd have to look it up myself, to be honest. I think it's pin 7. Anyway, well, you can look that up after. Okay, no need to spend more time on this. The other thing that I wanted to, while we're talking about LEDs, I noticed that D1 also. So I see there D1 is tied directly to the 12-volt supply, and then the current would flow through Q2 directly to ground. Again, that's a very non-typical thing to see with an LED, that you don't have a dropping resistor. Why does D1 not have a dropping resistor? Can you explain that?
Okay, I assume that with the transistor there.
Don't assume. Don't assume. Tell me why. Because you know this too, because we talked about this.
So we say because of the transistor, there was no need for dropping resistors anymore.
It has nothing to do with the transistor. If I took that transistor right out and replaced it with a short to ground, the LED would still work exactly the same way. And it would still work at 12 volts with no dropping resistor. Why?
Okay, yes.
Flashing, right? Okay, why?
Yes, because the LED already has a built-in resistors.
Aha. So what is the nominal voltage that this LED is designed to work at? And it's actually a range, if you remember.
0 to 5 volt.
I don't think it would work very well at 0 volts. And if it would be a maximum of 5, you definitely would need the limiting resistor, because you're at a 12 volt supply here. Right? Your LED would only blink once if you applied 12 volts to a 5 volt LED.
I can't remember.
Can't remember? Okay. Well, this one had an operating range of somewhere between 10 and 20 volts, a range, right? If you remember.
Yeah.
Okay.
Yes.
Any other questions?
Well, I'm just going to state my follow-up question, but I know we're running out of time here. So my follow-up question was derivative of yours, Ron, was the feed from pin 1 on top there to the 2 transistors. Do you think that has an effect on the performance of the IC? And did you check that it was within the parameters of that IC? Because there is the limits to that. So do you think that that LED coming on and the buzzer, I mean, that's additional to the current that needs to be sunk by the or not sunk, supplied or going through the LED there, the original LED, right? Because we're kind of diverting here. The device sinks current. All right, it sinks current through the diodes, but we're also trying to feed these 2 transistors while we're at it, right? So it's kind of. So did you go look up on the parameter sheet if you were still within the, the parameters of that IC? Because there are limits to it.
Yes, I checked that, and
so what's the maximum that one of those pins can sink? Do you recall?
2.2 volts.
No, we're talking current here, not.
I'm sorry. I'm sorry. No. Okay, no more than 10 milliamps.
Yeah, at 5 volts, no more than 10. Actually, the maximum, that's a typical number. The maximum is 13 milliamps. And that's fine. That probably you can get away with that. But the key is the next parameter over that you should look at is the LED current difference. In other words, the difference in current between the different branches. And that one is not as much as people would think it is. If you're drawing the 10 or 13 milliamps there, it's about only about 1.5 milliamps. So you got to make sure that when you're drawing current for those transistors, okay, that you're not drawing more than that 1.5 milliamp that's required for all the other LEDs, because they're not going to get loaded as much either, right? So if not, what happens is your device falls out of regulation. Mr. Broad was talking about current regulation. It'll fall out of regulation, and then it won't work like you expect it to work. Then the LEDs won't be turning on and off, and they won't be as bright as you want and things like that. So you got to be careful of that. This is a great little circuit, just that you got to make sure that you don't work outside of its parameters, or then it'll start doing some pretty strange things.
Yes. Yes. Thank you, Mr. Metcalf.
All right. So, I guess any other questions at this point? All right. So that concludes. Oh, no, sorry, Don.
No, I'm just going to say that's good.
So that concludes our presentations for today. I'd like to thank all the presenters for their hard work and effort. They did a great job. They shared their knowledge with us, and I'm sure they feel somewhat of a relief from the experience. Tomorrow we will have presentations in the morning. I believe I didn't look there, but I think there's 3 presentations tomorrow morning. Maybe possibly 4, but definitely 3. So please join us again at 8:30 for the presentations. And again, I'll just remind everybody that the YouTube stream is a new URL, so make sure you select the one off the schedule that is marked for day 4 or Friday. I'm not sure if it's marked as day 4 or Friday, but either way, so use that. And the other streams are available at any time for you to review if you want to. We have had a bit of problems with the YouTube stream, so if there is a presentation there that is not available, you can try to contact us, or you can contact us, and we'll see what we can do for that. We've had a bit of issues on our side too here for recording, so some of them may not be available, unfortunately, on between YouTube and Teams, but the majority of them are. So by all means, get a hold of us, and we'll gladly supply you with what we have recorded. So once again, thanks everybody, and we'll see everyone tomorrow morning.